Hello there, and welcome to Physics with William, where curiosity can slow down, difficult ideas are given room to breathe, and science is allowed to take the quieter route. Tonight, we are going to spend some time with a material that looks as though it should not exist. It can appear solid, yet seem barely present. It can rest on the surface of a flower without crushing the petals. It can trap heat, block cold, absorb oil, carry electricity, and in some forms weigh less than almost any solid ever made. Its name is Aerogel, and one especially unusual member of this family is often called Aerographene. Before we get too far into this strange world of almost weightless matter, I would love to know where you're listening from tonight. Are you somewhere quiet with the lights low and the day finally behind you, or are you still in the middle of things? Perhaps pretending to be productive while learning about a material that is mostly empty space. And what is the lightest object you can see near you right now? A sheet of paper, a feather, a dry leaf, perhaps a small piece of tissue that has somehow escaped from its box and attached itself to your sleeve. Whatever it is, Aerogel makes ordinary light objects feel almost enthusiastic about their weight. If you find this kind of slow scientific journey relaxing, interesting, or simply useful company while you settle down, you can give the video a like and subscribe to the channel. It helps more people find this quiet corner of physics, and it also reassures the mysterious machinery behind the screen that stories about unusual materials deserve to be shared. No one fully understands the machinery, of course. It may be powered by mathematics, advertising, or a very tired hamster. We can leave that problem for another evening. For now, get comfortable and picture a small block sitting on a table. It has a pale blue tint. Light passes through it, but not clearly. It looks a little like smoke that has been asked to hold still. If you reach toward it, your eyes might tell you to expect glass, ice, or perhaps some kind of hard foam. Then you lifted it, and for a moment you might wonder whether you had actually picked it up. It would feel unexpectedly light, as though the material had forgotten to include most of itself. That first impression is the key to aerogel. Aerogel is not a single substance in the same way that copper, wood, or glass is a single familiar substance. It is a type of structure. Many different materials can be made into aerogels, including silica, carbon, metal oxides, polymers, and forms built from graphene. What they have in common is that they contain an enormous network of tiny solid branches surrounding an even larger amount of empty space. In many aerogels, nearly all the volume is air or another gas. The solid part forms a fine internal skeleton, and that skeleton is so thin and spread out that the finished material can have an extremely low density. This is why aerogel can seem confusing when you first see it. We usually connect solidity with weight. A brick feels solid because there is a great deal of matter packed into a small volume. A steel tool feels even more convincing. It does not merely sit in your hand, it announces itself. Aerogel is different. It can keep a shape, resist certain forces and behave as a solid, while containing far less matter than its size suggests. It is a solid that has been designed around absence. That does not mean there is nothing there. The empty space is held together by a real structure, and the details of that structure decide what the aerogel can do. A silica aerogel may be an excellent thermal insulator. A carbon aerogel may conduct electricity. A graphene aerogel may combine low weight with useful strength, flexibility, and a large internal surface area. Two samples may look equally light and delicate, while behaving very differently once they are heated, compressed, soaked, charged, or placed under stress. The word aerogel itself gives us a useful clue. A gel is usually a solid network filled with liquid. Think of jelly, although scientific gels can be much less edible and far more expensive. In an aerogel, the liquid inside that network has been removed and replaced by gas without allowing the delicate structure to collapse. The result is a dry, highly porous solid. That sounds straightforward when said quickly, rather like explaining that baking is simply mixing ingredients and adding heat. In practice, preserving such a fragile internal network can be difficult, and the methods used to do it are one of the reasons aerogels became famous among scientists and engineers. The earliest aerogels were not made from graphene because graphene itself had not yet entered modern material science. The first successful examples were made many decades ago after a challenge between two researchers about whether the liquid in a gel could be removed without shrinking the solid framework. It was the kind of scientific question that begins with curiosity and ends with someone building unusual equipment in a laboratory. The answer turned out to be yes, but only if the liquid was removed carefully enough to avoid the forces that normally pull the structure inward. Imagine a wet sponge. If you squeeze out the water, the sponge may change shape, but it can spring back because its walls are thick and flexible. Now imagine a sponge whose walls are far thinner than a human hair, with spaces so small that ordinary drying forces can tear or crush the entire network. That is much closer to the problem. The liquid must leave, but it must do so without dragging the structure down with it. Scientists learned to use special drying methods that avoid the destructive boundary between liquid and gas. Later techniques improved the process, reduced costs, and allowed new types of aerogel to be produced. The result was a material with properties that seemed almost contradictory. It was extremely light, yet it could remain solid. It allowed light through, yet it scattered enough of that light to produce a soft, cloudy appearance. It could feel fragile, yet it could protect equipment from intense heat. It was mostly open space, yet the small amount of solid matter inside it created an enormous internal area. A piece that fits in your hand can contain a complicated maze of surfaces hidden at scales too small to see. That large internal surface matters because many physical and chemical processes happen at surfaces. Absorption, adsorption, electrical storage, chemical reactions and interactions with gases or liquids can all become more effective when a material offers more area for those interactions to occur. Aerogel does not simply provide an outside surface like the skin of an apple. It provides countless internal surfaces, folding through the structure in a network of pores. To anything small enough to enter, the material is less like a block and more like a vast landscape of narrow passages. This is where carbon-based aerogels become especially interesting. Carbon is remarkably adaptable. It appears in soft graphite, hard diamond, microscopic tubes, thin sheets, porous networks, and many other arrangements. The same basic element can produce materials with very different properties depending on how its atoms are connected. Graphene is one of those arrangements. It is a sheet of carbon only one atom thick, arranged in a repeating pattern. On its own, graphene is known for being strong, light, and electrically conductive. But a single sheet is not very useful if you want a three-dimensional object. It tends to bend, fold, stack, or stick to other sheets. Aerographene is one answer to that problem. Instead of treating graphene as a flat sheet, researchers build it into a three-dimensional porous network. The exact name can vary. You may hear graphene aerogel, graphene-based aerogel, or aerographene. These terms are sometimes used broadly, and different research groups may produce materials with different structures and properties. The basic idea, however, is easy to understand. Very thin carbon-based sheets form a connected framework while most of the volume remains empty. When this is done well, the material can become extraordinarily light. Some graphene-based aerogels have been reported with densities lower than other famous ultralight solids, which is why headlines often call them the lightest materials in the world. The phrase lightest material in the universe sounds even more dramatic, and it certainly knows how to attract attention. Still, it helps to be precise. Scientists compare materials under defined conditions, and records can depend on how density is measured, how much of the sample is counted, whether the material is dry, and what kind of structure has been produced. It is safer to say that aerographene belongs to the group of the lightest solid materials ever made. Even that careful version is impressive. A normal object feels light when it contains a small amount of matter. Aerographene goes further by arranging that small amount of matter into a large open framework. The material may occupy the space of a small cube, while containing only a tiny mass of carbon. If you place a sample on a delicate plant, the plant may support it easily. If you compare it with ordinary foam, the foam can suddenly seem heavy. This is not because graphene has escaped gravity. It is because the structure uses matter with extreme efficiency. The word efficiency is important here. In engineering, strength is not always about making something thick and heavy. Sometimes the better approach is to place material only where it is needed. A bridge does not have to be a solid block of steel. It uses beams, supports, and open spaces to carry loads. Bones do something similar. The outside can be dense, while the inside contains a lighter network that provides support without unnecessary weight. Aerographene follows the same broad principle at a much smaller scale. It creates a framework that can span a volume while using very little solid material. Of course, being light does not automatically make something useful. A soap bubble is light, but it is not a good choice for protecting a spacecraft. A cobweb is light, but few people would build a battery from one. The real interest in aerographene comes from the combination of low density with other properties. Depending on how it is made, it may be flexible, compressible, conductive, absorbent, or resistant to certain kinds of damage. It may recover after being squeezed. It may take in oils while rejecting water. It may help create lightweight electrodes for energy storage. It may act as a support for other chemicals or particles. It may become part of sensors that respond to pressure, strain, heat, or gases. These possibilities come from structure as much as composition. The same carbon atoms can behave differently when arranged in a dense block, a thin sheet, or a branching porous network. That is one of the central lessons of material science. What something is made from matters, but how it is arranged can matter just as much. Flour, water, and yeast can become bread, but the result depends heavily on what you do with them. Carbon has a wider menu. There is also something useful about the way aerogels slow the movement of heat. Heat travels through materials in several ways. In a dense solid, vibrations and moving particles can carry energy from one region to another. In a gas, moving molecules can transfer energy through collisions. Air itself is already a fairly poor conductor of heat when it is trapped and prevented from circulating. Aerogel takes advantage of that. Its tiny pores limit the movement of gas, while its delicate solid framework provides only narrow paths for heat to travel. This can make some aerogels exceptional insulators. You may have seen demonstrations in which a flower is protected from a flame by a thin layer of aerogel, or a piece of chocolate remains solid while heat is applied nearby. Demonstrations are designed to be memorable, and they do not show every limitation of the material, but they reveal something important. A small amount of the right structure can interrupt the flow of heat surprisingly well. This is why aerogels have been studied for buildings, industrial equipment, scientific instruments, and spacecraft. Space is a natural place to use materials that save weight. Every extra amount of mass sent upward requires energy, fuel, planning, and money. Engineers therefore care deeply about materials that can insulate without becoming bulky or heavy. Aerogels have been used in missions and instruments where thermal control matters. They have also been used to capture tiny particles moving at high speed. A particle entering a normal solid might shatter or be destroyed. Entering a very light porous aerogel, it can slow more gradually, leaving a track through this material that scientists can later examine. There is a nice contradiction in that use. Aerogel is so insubstantial that it can catch material from space. It does not stop the particle by presenting a hard wall. It gives the particle a long, gentle path through a maze of fine structure. The impact energy is spread out, and the visitor is brought to rest without the same level of violent damage. It is less like hitting a brick wall and more like running into a room filled with an unreasonable number of curtains. Graphene-based aerogels add another set of possibilities because carbon can carry electrical charge. Their porous networks can allow ions or molecules to move through while electrons travel along the solid framework. This is useful in devices that store energy or detect changes in the environment. A large internal surface gives more places for reactions or charge storage. Low mass can improve performance where weight matters. Flexibility can help when a device must bend or survive repeated pressure. At the same time, it is important not to treat aerographene as a magical answer to every engineering problem. Materials that perform beautifully in a laboratory can be difficult to manufacture in large quantities. A sample may be light but expensive. It may have excellent properties in one direction and weaker behavior in another. It may absorb moisture, suffer damage during handling, or require careful processing. Scaling up production can introduce defects. Joining the material to other components may be harder than making the material itself. Engineers spend a great deal of time solving problems that do not appear in dramatic photographs. This is one reason the story of Aerogel is more interesting than a simple record for lightness. The record catches our attention, but the real work lies in understanding how to control the structure. How large should the pores be? How thick should the graphene walls become? How can the sheets be kept apart instead of collapsing into a dense stack? How can the network remain strong while using less material? How can the process be made consistent from one batch to the next? How can it be produced without using too much energy, time, or costly equipment? Those questions move us away from the image of a mysterious floating solid and toward the practical science behind it. The material is not light because someone removed weight in the ordinary sense. It is light because its makers learned how to create and preserve a network that is mostly space. They begin with particles, sheets, or molecules dispersed through a liquid. They encourage those pieces to connect. They form a gel. Then they remove the liquid while trying to keep the internal framework intact. Each stage can change the final result. A small change in concentration can alter the thickness of the walls. A different drying method can shrink the pores. A change in temperature can affect how the network forms. Added chemicals can improve bonding or introduce new functions. Heat treatment can strengthen the carbon structure or change its conductivity. The final object may look simple, but its history is written throughout its microscopic architecture. This is also why two things called graphene aerogel may not be identical. One may spring back after compression. Another may crumble. One may absorb oil quickly. Another may be designed for electrical storage. One may contain nearly pure graphene-based material. Another may include polymers, metals, oxides, or other forms of carbon. Names are useful, but they can hide a great deal of complexity. Still, the basic idea remains easy to appreciate. Take a material famous for strength and conductivity. Spread it into very thin sheets. Connect those sheets into a three-dimensional framework. Preserve the empty spaces between them. The result is an object that uses a tiny amount of matter to create a surprisingly large and useful structure. Perhaps that is what makes aerographene feel so unusual. We are used to thinking that more material means more capability. Thicker walls, heavier tools, stronger supports. Aerographene suggests another approach. Remove what is not needed. Keep the connections that carry force, heat, electricity, or chemical activity. Let the empty space become part of the design. As you settle a little more deeply and the room around you becomes quieter, keep that image in mind. A solid that is mostly air. A carbon framework so light that a small sample can be supported by the softest surface. A material that looks fragile but may hide useful strength, enormous internal area, and paths for heat, electricity, liquids, and gases. We have only looked at it from the outside so far. The next step is to move closer and ask what aerogel actually is at the level of its structure, why it gained the nickname frozen smoke, and how something can be both present enough to hold and empty enough to feel almost weightless. To understand why aerogel feels so unusual, it helps to forget the photographs for a moment. Forget the pale blue blocks balanced on flower petals, the dramatic flames held safely above delicate objects, and the samples that appear to float on air. Those images are impressive, but they can make aerogel seem like a mysterious substance discovered in a distant corner of physics. In reality, the basic idea is surprisingly practical. Aerogel is a solid framework containing an enormous number of tiny pores, and those pores are filled with gas instead of liquid. That description may not sound especially dramatic. Many ordinary materials contain gas-filled spaces. Bread contains bubbles. Foam contains cells. A kitchen sponge is filled with open passages. Even wood contains small channels that once transported water through a living tree. Yet aerogel pushes this familiar idea to an extreme. Its pores can be incredibly small. Its internal framework can be extraordinarily thin, and the amount of empty space inside it can account for nearly all of its volume. When you hold a piece of aerogel, you're not holding a block of air. Air alone cannot keep the shape of a brick, support a load, or remain sitting politely on a table. You're holding a continuous solid network that stretches throughout the object. That network may contain silica, carbon, a polymer, a metal oxide, or some combination of materials. The network is real, but it is so fine and so widely separated by pores that the sample contains very little solid matter compared with an ordinary block of the same size. Picture a large building supported by a carefully arranged system of beams. Most of the interior is open space, yet the beams connect from one side to another and allow the building to stand. An aerogel works according to a similar principle, although its internal supports are far smaller and much more irregular. Instead of rooms and corridors, it contains microscopic branches, particles, sheets, and openings. The arrangement differs from one aerogel to another, but the general result is the same. A small amount of solid material creates a structure that occupies a much larger volume. This is why calling aerogel a material can be slightly misleading. Aerogel is better understood as a form that many materials can take. Glass and silica are closely related, but silica aerogel behaves very differently from a window. Carbon can become graphite, diamond, charcoal, graphene, or carbon aerogel. Certain polymers can become dense plastics or light porous aerogels. The chemical ingredients matter, but the internal architecture matters just as much. The most familiar variety is silica aerogel. Silica is made from silicon and oxygen, and is also a major ingredient in ordinary glass. If silica is melted and cooled into a dense form, it can become clear and hard. If it is arranged into an aerogel, it becomes extremely porous, very light, and often translucent. It may look like a cloudy blue piece of glass, but the resemblance ends quickly once you pick it up. A block of glass feels heavy for its size because its atoms are packed into a dense network. A silica aerogel uses related chemical building blocks, yet most of the space between them has been opened into pores. The solid framework may account for only a small fraction of the sample. This changes nearly every property we notice. The weight falls dramatically. The movement of heat becomes difficult. Light scatters through the tiny structure. The surface area hidden inside the material becomes enormous. At the same time, the thin framework can make the sample fragile. The nickname frozen smoke comes from this appearance. A pale silica aerogel can look like a cloud that has somehow become firm enough to hold. It seems smoky because light does not travel through it as cleanly as it travels through ordinary glass. The internal structure sends some of the light in different directions. Shorter wavelengths are scattered more strongly, which can give the material a softer blue appearance when viewed under certain conditions. The same broad effect helps make the daytime sky look blue. The comparison is useful, although an aerogel is not simply a miniature piece of sky. Its structure is much more complicated, and its appearance changes with thickness, lighting, composition, and the way it was produced. A thin sample may look almost transparent. A thicker one may appear milky or deeply blue. When light shines through it from behind, warmer colours may become more visible because much of the blue light has been scattered away before reaching your eyes. Smoke also scatters light, but smoke is a collection of particles drifting through gas. It changes shape, spreads out and disappears, and aerogel remains a solid. Its particles are joined into a network that extends across the sample. You can place it on a surface, cut it, carry it, and measure its dimensions. It does not drift toward the ceiling or escape through an open window, which is fortunate because laboratories already contain enough things that are difficult to find. The word frozen can also cause confusion. Most aerogels are not frozen in the ordinary sense. They do not need to remain cold, and they are not blocks of solidified gas. The nickname refers to the way their appearance seems fixed in place. Something that looks soft and temporary has become stable. Smoke appears to have paused. The name aerogel itself tells a more accurate story. It begins with a gel. A gel contains a continuous solid network spread through a liquid. The solid part may be present in a very small amount, but it connects strongly enough to prevent the liquid from flowing freely. Jelly is a familiar example. Its liquid is trapped within a network of molecules, allowing the whole thing to wobble without pouring across the plate. Scientific gels can be made from many substances, and most are not intended for dessert. Some begin as a liquid mixture containing tiny particles or chemical building blocks. As those pieces react or join together, they create a connected network. Once that network reaches across the entire container, the liquid loses its ability to move freely. The result is a wet gel. At this stage, the object may already have the shape of the aerogel that will eventually emerge. It might be a block, a thin sheet, a cylinder, a bead, or a more complicated form. However, its pores are still filled with a liquid. The difficult step is removing that liquid while preserving the fragile network around it. If the liquid simply evaporates from an ordinary wet gel, the retreating surface of the liquid can pull on the tiny walls of the structure. The forces involved may shrink, bend, or collapse the pores. The result can still be a porous solid, but it may be denser and much smaller than the original gel. Aerogel production uses drying methods designed to reduce or avoid that collapse. We will follow that process more closely soon because it is one of the cleverest parts of the story. For the moment, the important point is that an aerogel is not created by drilling millions of tiny holes into a solid block. The pores develop as part of the gel itself. The solid network forms around liquid, and the liquid is later replaced by gas while much of the network remains in place. This explains why the pores are so deeply connected to the identity of the material. They are not damage, decoration, or empty space added afterward. They are part of the original architecture. Remove the pores by crushing the sample, and many of the unusual properties disappear. The chemical ingredients may remain, but the material is no longer behaving as the same aerogel. The scale of these pores is difficult to imagine. They're often far smaller than anything the human eye can see. A sample that looks smooth from across a room may contain a tangled landscape of particles, branches, sheets, and channels. Under a powerful microscope, the solid part may resemble a cluster of tiny beads connected into chains, a collection of thin walls, or a web that has grown in every direction. There is no single internal shape shared by all aerogels. A silica aerogel may be built from connected silica particles. A polymer aerogel may contain long molecular chains joined into a network. A carbon aerogel may form branching clusters of carbon. A graphene-based aerogel may contain thin, folded sheets joined into open cells. The word aerogel describes their highly porous state, not one exact microscopic design. Porosity tells us how much of a material consists of empty space. In an ordinary dense solid, porosity may be low. In aerogel, it can be extremely high. This does not mean the pores are perfectly empty. Under normal conditions, they contain air or another gas. If the material is placed in a vacuum, much of that gas can be removed. If it is placed in a liquid, some pores may fill, depending on how the surface interacts with that liquid. This last detail is important because aerogels can be designed to attract or repel different substances. Some untreated silica aerogels readily interact with water. Moisture can enter their pores and affect their performance. Scientists can modify the surface to make it more resistant to water. Carbon-based aerogels can often be prepared to absorb oils and organic liquids. which has led to interest in cleaning spills and separating liquids. The difference between absorbing and adsorbing is worth a quiet pause. Absorption usually means that a substance enters the volume of another material, rather like water entering a sponge. Adsorption means that molecules attach to surfaces. Aerogels can do both, but their enormous internal surface makes adsorption especially important. Gas or liquid molecules can move into the pores and encounter solid surfaces at almost every turn. A small piece of aerogel may contain an internal surface area much larger than its visible outer surface. If that hidden area could somehow be unfolded and laid flat, it could cover a surprisingly large space. This gives scientists many places to attach catalysts, store electrical charge, capture molecules, or support chemical reactions. The aerogel appears simple in your hand, but to a molecule moving through it, the inside is a very large place. The pores also explain why many aerogels slow the movement of heat. Heat can travel through a solid framework, through gas, and through radiation. Aerogel interferes with all of these routes in different ways. The solid framework is thin, so there is relatively little material available to carry heat directly from one side to the other. The gas sits inside extremely small pores, which limits the way its molecules move and collide. Convection, the circulating motion that transports heat through larger pockets of gas, is greatly restricted because there is not enough room for the gas to form useful currents. Certain aerogels also scatter or absorb some thermal radiation. This combination can make aerogel an excellent insulator. It does not produce cold or destroy heat. It simply makes heat transfer more difficult. Place a source of heat on one side and the energy takes longer to reach the other. The same principle works in reverse. A cold object surrounded by aerogel can be protected from warmer surroundings. The material cannot block heat forever. Given enough time, energy will still move through it. Its performance also depends on temperature, pressure, thickness, composition, and physical condition. Cracks, compression, moisture, and gaps around the material can reduce its effectiveness. Aerogel is impressive, but it has not negotiated a private exemption from thermodynamics. The relationship between air and insulation is already familiar from winter clothing. A thick coat keeps you warm partly by trapping pockets of air. Double-glazed windows use a sealed space between panes to slow heat transfer. Fiberglass insulation holds air inside a network of fibers. Aerogel follows the same general strategy while reducing the scale of the spaces and the amount of solid material. Silica aerogel often feels unexpectedly cold when first touched. That does not mean it has a naturally low temperature. Objects in the same room eventually reach roughly the same surrounding temperature. The sensation depends on how heat moves between your skin and the object. Aerogel conducts heat poorly, so the experience can differ from touching metal, glass, or stone. The effect is also influenced by surface texture and by any dust released from the sample. Handling some aerogels requires care. Traditional silica aerogel can be brittle. Press a finger into a fragile sample, and the thin network may crack or crumble. Small particles can form on the surface, leaving a powdery feeling. Protective equipment may be appropriate in a laboratory or workshop, particularly when cutting or processing the material. The object may look like a harmless piece of cloud, but lungs are not improved by collecting clouds of fine dust. Brittleness is not a necessary property of every aerogel. Researchers can reinforce the structure with fibers or polymers. Some polymer aerogels are flexible. Certain carbon and graphene-based aerogels can be compressed and then recover much of their shape. Others are designed to withstand repeated squeezing. The behavior depends on the strength of the solid framework and the geometry of the pores. A structure made from tiny rigid particles may break when bent. A structure made from flexible sheets may buckle and unfold. A network with carefully arranged cells can distribute pressure more effectively than a random fragile web. The density also matters. Adding more solid material can increase strength, but it also increases weight and may change the insulating behavior. Designing an aerogel often involves balancing several properties that do not improve together. The phrase lightest material can therefore hide an important trade-off. Removing more solid matter usually lowers density, but it can also weaken the structure. At some point, the network may become too sparse to support itself. The achievement is not simply making something lighter, it is making something lighter while preserving enough connection to remain useful. Graphene-based aerogels approach this problem with thin carbon sheets. Graphene itself consists of carbon atoms joined in a single layer. A perfect sheet is extremely thin and can be very strong within its plane. It also conducts electricity and heat effectively. Turning that sheet into a three-dimensional aerogel changes the situation. Individual sheets can bend, wrinkle, and stack together. If they collapse into a dense pile, much of the open space and accessible surface is lost. Researchers therefore try to connect or separate the sheets so they form a stable network. The finished structure may resemble a foam, with walls made from overlapping layers of graphene-based material. The term aerographene is often used for ultra-light three-dimensional networks built largely from graphene or reduced graphene oxide. It does not always refer to one standard recipe. One sample may contain additional carbon structures, polymers, or reinforcing materials. Another may have been reduced at high temperature to remove oxygen-containing groups. The name tells us the broad family, but the preparation method tells us how the material will actually behave. Unlike pale silica aerogel, graphene-based aerogel is usually dark. Carbon absorbs a broad range of visible light, so the material may appear black even though very little carbon is present. This creates another visual surprise. We associate black objects with heaviness and solidity. A dark graphene aerogel may look like a lump of charcoal until it is lifted. Then the expected weight never arrives. The black appearance can also help the material absorb light and convert some of that energy into heat. This can be useful in systems designed for heating, evaporation, sensing, or energy conversion. At the same time, the porous structure may remain a poor conductor of heat across the entire sample because the solid paths are sparse and interrupted by countless interfaces. A single graphene sheet can carry heat very well, while a large aerogel made from many folded and loosely connected sheets may behave quite differently. There is no contradiction here. Material properties depend on scale and arrangement. A copper wire conducts electricity well, but a pile of copper dust may have unreliable connections between particles. A sheet of paper tears easily in one direction, while a tightly rolled paper tube can support a surprising load. Graphene has remarkable properties, but an aerographene object inherits only some of them, and those properties are altered by every wrinkle, contact, pore, defect, and added ingredient. Electrical conductivity follows a similar pattern. For current to move through the aerogel, the carbon sheets must form connected paths. If gaps interrupt those paths, conductivity falls. If the sheets contact each other well and have been processed to restore their carbon network, current can travel more easily. Compression may bring sheets closer together and change the electrical resistance. This allows some graphene aerogels to act as pressure or strain sensors. Imagine a soft block placed beneath a small load. As it is squeezed, its internal sheets bend and make new contacts. The electrical signal changes. Remove the load, and the network moves back toward its earlier shape. By measuring the signal, a device can estimate how much pressure was applied. This principle could be used in wearable sensors, soft machines, motion detection, or equipment that must notice very gentle forces. The pores can also hold liquids containing charged particles. The large internal surface then gives those particles many places to interact with the carbon framework. This is useful in the electrodes for batteries and capacitors. The aerogel itself does not automatically become a perfect energy storage device. It must be combined with suitable chemicals designed for efficient transport, connected to electrical contacts, and protected from damage. Still, its structure provides an attractive starting point. When people first encounter aerogel, they often ask whether it floats in air. Most aerogels do not. A solid can be extraordinarily light and still be denser than the surrounding atmosphere. Even a material whose average density is reported below that of air faces practical complications. Air may enter its open pores, adding effective mass, and the solid framework still responds to gravity. A sample placed gently in the room will not normally rise toward the ceiling like a helium balloon. The confusion comes from comparing the density of the solid framework and pores with the density of air. An open aerogel does not seal a separate volume of lighter gas in the way a balloon does. The surrounding air can pass through or occupy its pores. Without a closed skin and a useful difference in the mass of the enclosed gas, there is little buoyant lift. The material may be light enough to move in a faint breeze, but that is not the same as floating by itself. It is equally important not to confuse aerogel with ordinary foam. Foam usually contains bubbles separated by thicker walls. Some foams have closed cells, while others have open passages. Their pores are often much larger than those in traditional aerogels. Aerogels tend to contain finer structures and much greater internal surface area. The boundary is not always perfectly clear, and researchers sometimes use terms such as aerogel, foam, sponge, and porous monolith in overlapping ways. What matters is the actual structure and method of preparation. Nor is aerogel necessarily soft. The word gel makes many people expect something wet and wobbly. Once the liquid has been removed, the result can feel dry, rigid, springy, or brittle. A silica aerogel may crack like a delicate ceramic. A polymer aerogel may flex. A graphene aerogel may compress like a very light sponge. The family contains materials with very different personalities. Their shared feature is not texture but architecture. They begin with a network formed in a liquid and end as a porous solid whose internal spaces contain gas. That process preserves a level of openness that ordinary drying often destroys. Everything else follows from the chemistry and the design. Now the pale block from our earlier image becomes easier to understand. It is not solid smoke, frozen air, or a piece of matter that has somehow lost its mass. It is a very small skeleton occupying a relatively large space. Light scatters from the skeleton. Heat struggles through it. Gas sits inside its pores. Molecules find vast internal surfaces. The network gives it shape, and the lack of unnecessary material gives it lightness. Aerographene takes the same structural idea and builds the skeleton from thin carbon-based sheets. Its darkness, conductivity, flexibility, and ability to interact with oils or charged particles come from those sheets and from the way they connect. Its lightness comes from everything that has been left between them. The object we see at the end is therefore only a record of an earlier liquid structure. Every pore marks a place once occupied by solvent. Every thin wall shows where particles or sheets joined while suspended in that solvent. Every crack or wrinkle reveals something about the stresses of drying. To learn why one sample remains open while another collapses, we need to return to the wet gel and watch what happens as the liquid begins to leave. The liquid inside a wet gel cannot simply be poured away. It is held throughout the structure in countless microscopic spaces, surrounding branches that may be far thinner than anything the eye can see. Removing it without damaging those branches is the central challenge of making aerogel. The process is less like emptying a glass, and more like trying to remove all the water from a cloud, while asking every droplet to leave the shape of the cloud untouched. Everything begins with a liquid mixture. For a traditional silica aerogel, the mixture contains chemical building blocks that can form silica, along with a solvent and small amounts of other substances that control the reaction. The liquid may look completely ordinary at first. It can be clear and still, with no obvious sign that a solid object is about to grow inside it. Yet on the scale of molecules, connections are beginning to form. The silica building blocks react with water and then begin joining to one another. At first they form tiny clusters. Those clusters grow, branch, and meet other clusters. Given the right conditions, the connections eventually spread across the entire container. The liquid is no longer simply a liquid with particles floating inside it. A continuous solid network now reaches from one side to the other. This transformation is called gelation. Before gelation, the mixture can flow. After gelation, it holds its shape even though most of it is still liquid. The change can happen quickly or slowly depending on the ingredients, temperature, acidity, concentration, and preparation method. A mixture may remain fluid long enough to be poured into a mould, then gradually become firm. In other cases, the reaction moves so quickly that anyone working with it must be ready. Chemistry, like a cat near an open cupboard, does not always wait for permission. The mould determines the general shape of the final aerogel. A scientist might prepare a thin panel, a cylinder, a small bead, a blanket, or a sample designed to fit inside an instrument. The gel can also form around fibres, particles, or other supporting materials. This allows the finished aerogel to gain strength or perform an additional function. Once the network has formed, the wet gel often needs time to age. Aging sounds peaceful, and in this case it usually means allowing the structure to become stronger before drying begins. Chemical reactions continue inside the gel. New connections form between neighbouring particles. Thin branches may thicken slightly. Weak regions can become more stable. A newly formed gel can be surprisingly delicate. It may hold together, but only just. Moving it too quickly, exposing it to the wrong liquid, or allowing it to dry at the surface can cause cracks. Aging gives the network a better chance of surviving what comes next. The liquid inside the pores may also need to be exchanged for a different solvent. The original mixture can contain water, alcohol, unreacted chemicals, and products left behind by the gel-forming reactions. Some of these substances are unsuitable for the chosen drying method. The gel is therefore placed in a fresh liquid, allowing the unwanted contents of the pores to diffuse outward, while the new solvent moves inward. This exchange may be repeated several times. Each round removes more of the original liquid. Nothing dramatic appears to happen from the outside. The gel sits quietly in a container, looking as though it has achieved very little. Inside, however, molecules are slowly trading places throughout an enormous network of narrow passages. Patience matters because rushing the exchange can create uneven conditions. The outside of the gel may change faster than the centre. Different parts may shrink at different rates. Stress can build until the sample cracks. Large pieces are particularly difficult because the distance from the centre to the surface is greater. A small laboratory sample might exchange its liquid relatively quickly, while a thick industrial panel requires much more careful control. After the pores contain a suitable solvent, drying can begin. This is the moment that separates an aerogel from an ordinary dried gel. When a normal liquid evaporates, it develops a curved surface inside each tiny pore. Surface tension pulls along that boundary. In a large, sturdy container, the force is harmless. In a microscopic network made from fine branches, it can become destructive. The receding liquid behaves like countless tiny hands pulling inward on every part of the structure. A wet towel survives ordinary drying because its fibres are large and flexible. A delicate gel network may not. As the liquid retreats, the pores can collapse. The sample shrinks, hardens, and sometimes cracks into pieces. The result is called a Aerogel, a dried gel that has lost a significant amount of its original pore structure. A Aerogel can still be useful. It may remain porous and serve as a catalyst support, coating, absorbent, or other functional material. It is not a failed object simply because it is not an aerogel. The difference lies in how much of the open network survives. To preserve that network, early aerogel makers turned to supercritical drying. The name sounds more alarming than the basic idea. It does not mean the drying process has become emotionally overwhelmed. It refers to a special state of matter reached by controlling temperature and pressure. Under ordinary conditions, a substance can exist as a liquid or a gas, with a visible boundary between the two. Raise the temperature and pressure in the right way, and the distinction eventually disappears. The substance enters a supercritical state. It is no longer clearly liquid and no longer clearly gas. Most importantly for aerogel production, there is no curved liquid surface inside the pores. Without that liquid surface, the destructive pull of surface tension can be avoided. The solvent can be brought into the supercritical state and then released as a gas. The network is left behind with far less shrinking than ordinary evaporation would cause. The process takes place inside a pressure vessel, built to withstand the required conditions. The wet gel is placed inside, surrounded by the appropriate fluid. Temperature and pressure are raised carefully. Once the fluid has crossed into the supercritical region, it is slowly vented from the vessel. The pressure cannot simply be dropped without control. A rapid release may cool the system, create uneven forces, or damage the sample. The fluid must leave the tiny pores gradually. When the vessel finally returns to ordinary conditions, the gel has become an aerogel. The liquid is gone, gas fills the pores, and much of the original solid skeleton remains. Some early methods used alcohol as the supercritical fluid. This required relatively high temperatures and introduced concerns about flammability. Later processes commonly use carbon dioxide, which can reach its supercritical state at more manageable temperatures and does not burn. Carbon dioxide does not always mix well with the water originally present in many gels, so solvent exchange becomes important. Water may first be replaced with alcohol. The alcohol is then gradually replaced with liquid carbon dioxide inside the pressure system. Once the pores contain mostly carbon dioxide, the temperature and pressure are adjusted for supercritical drying. The equipment is more complicated than an ordinary oven. It must control pressure safely, circulate fluids, prevent contamination, and maintain uniform conditions throughout the sample. This adds cost and makes large-scale production challenging. A small, beautiful aerogel block may therefore carry a surprisingly large history of pumps, valves, sealed chambers, and careful weighting. Supercritical drying is not the only option. Freeze drying can also preserve porous structures. In this method, the liquid inside the gel is frozen and then removed by allowing the solidified solvent to pass directly into a gas under reduced pressure. This avoids the usual liquid surface during drying, but freezing creates its own difficulties. Crystals grow inside the pores and can push the solid framework aside. Large crystals may produce large channels, while rapid freezing may create finer structures. The final material often has a different internal architecture from an aerogel made by supercritical drying. That difference can be useful. Scientists can control the direction of freezing so that crystals grow along preferred paths. Once those crystals are removed, the remaining solid contains aligned channels. Such a material may transport liquids easily in one direction, support certain mechanical loads, or serve as a carefully organized scaffold. Freeze drying is particularly common with polymer, carbon, and graphene-based gels. Water is often used as the liquid, and the frozen sample can be dried without the extreme pressure required for supercritical carbon dioxide. The result may be called an aerogel, a cryogel, or a porous foam depending on the preparation method and the language preferred by the research group. There are also ambient pressure drying methods. These attempt to remove the solvent under ordinary pressure while preventing the network from collapsing. To do this, scientists strengthen the gel, modify its surface, choose liquids with lower surface tension, or allow the structure to shrink and then spring back. Silica surfaces naturally contain chemical groups that can attract water and react with one another during drying. By replacing some of those groups with water-repelling ones, researchers can reduce unwanted bonding and help the network resist permanent collapse. The gel may shrink as the solvent leaves, then recover some of its original size afterward. Ambient pressure drying can reduce equipment costs and simplify production. It is attractive for building insulation and other uses where large quantities are needed. The trade-off is that the structure may shrink more than it would during supercritical drying. Achieving consistent results requires careful chemistry and close control of the process. Commercial aerogel blankets are often made by forming aerogel within a fibrous support. The fibres provide mechanical strength, while the aerogel fills spaces between them. The finished material can be rolled, cut and wrapped around pipes or equipment more easily than a fragile monolithic block. This changes the way the aerogel feels. Instead of holding a rigid piece of frozen smoke, a worker handles something closer to a thick, flexible fabric. It may still release dust when cut, and protective clothing can be needed, but it is much more practical for construction and industrial use. Producing graphene aerogel follows the same general story of network formation and careful drying, though the chemistry and structure are different. The starting material is often graphene oxide rather than perfectly pure graphene. Graphene oxide consists of thin carbon-based sheets carrying oxygen-containing groups. Those groups make the sheets easier to disperse in water. Pure graphene tends to attract other graphene sheets and stack together. Once stacked, it begins behaving more like a dense form of graphite, and much of the useful surface area disappears. By adding oxygen-containing groups, researchers make the sheets more compatible with water. They can be stirred or treated with sound until they spread through the liquid. The result may resemble a dark brown or black suspension. Each sheet is extremely thin, but there can be enormous numbers of them drifting through the container. The sheets must then be encouraged to connect into a three-dimensional network. This can happen through chemical reduction, heating, changes in acidity, added linking molecules, or interactions with polymers and other materials. As the sheets lose some of their oxygen groups, they become less comfortable remaining separately suspended in water. They begin approaching one another, folding, overlapping, and forming contacts. If the process is controlled well, they do not simply collapse into a dense lump. Instead, they create an open gel. Water remains trapped within the spaces between the connected sheets. The container now holds a graphene-based hydrogel, with hydro referring to the water inside it. The hydrogel may be soft enough to deform under its own weight. It can contain more than one kind of material. Polymers may strengthen the connections. Carbon nanotubes may act as supports or bridges between sheets. Metal particles or metal oxides may be added to create catalytic, magnetic, or energy storage properties. Once the wet network is ready, the water must be removed. Freeze drying is common because it is relatively accessible, and because the ice crystals can help create an open cellular structure. The hydrogel is frozen, sometimes rapidly and sometimes in a controlled direction. The ice is then removed under low pressure. What remains is a very light carbon framework. At this point, it may still contain a large amount of oxygen and other chemical groups. Additional heating can remove some of them, restore more of the carbon network, improve electrical conductivity, and strengthen contacts between sheets. Heating must be done in an atmosphere that prevents the carbon from simply burning. The sample may be placed in an inert gas or under reduced pressure. Temperature is increased according to a planned schedule. Too little treatment may leave poor conductivity. Too much may damage the structure, remove useful surface groups, or make production unnecessarily expensive. Other graphene aerogels are dried with supercritical carbon dioxide. This can preserve finer pores and reduce the damage caused by ice crystals. The choice depends on the desired properties, available equipment, cost, and scale. Researchers can also build the structure around a temporary template. A polymer foam, metal network, salt crystal, or other scaffold provides a shape. Graphene-based material coats the template, and the template is later removed. What remains is a hollow network that copies the original architecture. Templates offer control over pore size and connectivity. A random gel may contain a wide range of openings, while a prepared scaffold can produce a more regular pattern. The disadvantage is the extra processing. The template must be made, coated evenly, and removed without damaging the final structure. Another approach allows graphene material to grow directly on a metal foam. The metal provides a surface on which carbon layers can form. The metal is then dissolved away, leaving behind a delicate carbon copy. This can produce highly conductive networks with well-connected pathways, though the equipment and processing may be demanding. No matter which route is chosen, the finished density depends on how much solid material was present in the starting mixture and how much the network shrank during drying. A dilute mixture can produce a lighter aerogel, but the connections may be weak. A concentrated mixture produces thicker walls and greater strength, along with more weight. The challenge is not reaching the lowest possible number. A record-setting sample may be too fragile for practical use. It may survive only when handled with extreme care. An engineer designing an electrode, insulation panel, or spill absorbent may accept a slightly higher density in exchange for durability. Pore size matters as well. Very small pores are useful for thermal insulation and high surface area. Larger pores allow liquids and gases to move through more quickly. A battery electrode needs pathways for charged particles. An absorbent needs room for oil to enter. A pressure sensor needs a network that can deform and recover. Drying controls many of these features, but the structure is already being shaped long before the liquid leaves. The concentration of sheets, the speed of gelation, the type of solvent, the presence of additives, and the temperature all influence how the solid pieces meet. Imagine dropping a small number of sticks into a large room. They're unlikely to touch. Add more sticks, and eventually some begin forming connected paths. Continue adding them, and a network reaches from wall to wall. A gel forms when its microscopic building blocks reach this connected state. The contacts between those building blocks determine whether the network will survive. Weak contacts may separate during washing. Rigid contacts may snap during drying. Flexible contacts can bend, but they may not carry enough force. Designers try to create a structure that is connected, light, stable, and suited to its intended task. Impurities can change the outcome. Dust, salts, leftover reactants, or small differences in water quality may affect gelation. Temperature variations across a large mold can create uneven pores. Bubbles trapped during mixing may become cracks or cavities. Tiny defects can grow during drying until the final object breaks. This is why producing a large clear silica aerogel panel is much harder than producing a small sample. Every extra centimetre increases the distance that chemicals and solvents must travel. The centre may react differently from the surface. Pressure may not change uniformly. A flaw that would be invisible in a bead can ruin an entire panel. The finished aerogel may also require surface treatment, cutting, coating, or shaping. Some pieces are machined carefully with specialised tools. Others are formed directly in their final shape because later cutting would create too much damage. Dust can be removed, surfaces can be sealed, and additional materials can be added inside the pores. A catalyst might be deposited throughout the network. A water-repelling coating might protect the aerogel from humidity. Conductive particles could improve electrical performance. A flexible polymer could strengthen fragile branches. In this way, drying is not always the final manufacturing step. It is the moment when the open structure becomes available for further design. Seen from the outside, the process may still appear to have made very little. A container of liquid becomes a block so light that it barely seems to justify all the equipment used to produce it. Yet that apparent lack of substance is the achievement. The network has survived while almost everything surrounding it has been removed. The object is a preserved map of connections formed in liquid. A silica particle met another silica particle and remained joined. A graphene sheet folded against a neighbour and stayed there. A crystal grew, shaped a channel, and later vanished. A solvent filled every pore and then left without taking the framework with it. What remains is not simply a dried substance. It is a carefully protected arrangement of matter, one that could not have been carved from a dense block. Its useful qualities come from the route it travelled, from liquid mixture to wet gel, from wet gel to dry network, and from dry network to a material ready to insulate, absorb, conduct, sense, or support. The next time a photograph shows an aerogel resting on a flower or balanced on a thin blade of grass, The image carries more than a record of lightness. Hidden inside that pale or dark object is a manufacturing history shaped by chemical reactions, patient washing, controlled pressure, freezing, heating, and the careful removal of a liquid that once occupied nearly all of its volume. With the cloud now caught and dried, the remaining question lies inside it. The material may look uniform from a distance, but under magnification it becomes a complicated framework of walls, branches, junctions, folds, and passages. Those features decide whether it breaks, bends, insulates, conducts, or absorbs, and they lead us toward the architecture built from almost nothing. Seen from a distance, an aerogel can look almost uniform. A pale silica sample may appear like a cloudy block, while a graphene aerogel may resemble a piece of black foam. Under magnification, that simplicity disappears. The material becomes a crowded landscape of branches, sheets, bends, gaps, and junctions. Its behavior depends on how these features are arranged, how strongly they are connected, and how well they survive when the material is pressed, heated, soaked, or carried from one place to another. This internal design is often called the microstructure, although many of its most important features are much smaller than anything we would normally describe as microscopic. Some pores are tiny enough to be measured in billionths of a meter. Others are much larger and form channels that liquids or gases can travel through. An aerogel can contain several different pore sizes at once, with each scale contributing something different to the finished material. The solid part of a silica aerogel often begins as small particles joined into branching clusters. These clusters connect with other clusters until they form a continuous network. It is not a smooth set of walls like the inside of a soap bubble. It is closer to a tangled collection of beads, except the beads are extremely small and the connections between them can be narrow and fragile. Graphene aerogel has a different appearance. Its framework is usually formed from thin carbon-based sheets that fold, wrinkle, overlap, and connect. Some regions may look like crumpled paper. Others resemble the walls of an irregular sponge. The sheets can bridge across open spaces, bend around pores, and meet at junctions where force and electricity move from one part of the material to another. Those junctions matter more than the amount of material alone. A network can contain strong building blocks and still behave weakly if those building blocks are poorly connected. Imagine a pile of steel rods lying loosely on the floor. Each rod is strong, but the pile cannot support a roof because the rods do not form a stable structure. Join them at useful angles and the same amount of steel becomes a framework. Graphene is often introduced as an exceptionally strong material, but that description usually refers to a high-quality sheet tested under carefully controlled conditions. A graphene aerogel is not one perfect sheet stretched across an open space. It contains many sheets with folds, defects, edges, overlaps, and imperfect contacts. The strength of the final object depends on all of these features. When pressure is applied, the sheets may bend before the carbon bonds themselves are seriously stretched. This is useful because bending can absorb force without immediate breakage. The walls of the pores buckle inward, the open spaces become smaller, and neighbouring sheets move closer together. If the network has enough flexibility, it can recover when the pressure is removed. This recovery is one reason some graphene aerogels behave like very light sponges. They can be compressed to a fraction of their original size and then expand again. The process is not always perfect. Repeated compression can leave permanent changes. Weak contacts can separate, sheets can become stuck together, small cracks can grow. Still, a well-designed structure can survive many cycles. Silica aerogel usually behaves differently. Its network is often more rigid and brittle. When a thin silica branch reaches its bending limit, it may snap rather than fold. A crack can then move through nearby connections. The sample may fracture or release powder. The difference is similar to bending a dry twig and bending a strip of fabric. The twig holds its shape until it breaks. The fabric changes shape easily and may return afterward. Both are solids, but their internal structures respond to force in different ways. The shape of each pore also influences mechanical behaviour. Round openings distribute force differently from long narrow ones. Irregular cells may collapse in stages. Aligned channels can make the material stronger in one direction and weaker in another. If the pores are all arranged vertically, the sample may support pressure from above while bending more easily from the side. This directional behaviour is called anisotropy. It appears whenever a material has an internal arrangement that favours one direction. Wood is a familiar example. It splits more easily along the grain than across it. Some aerogels develop a grain of their own during freezing, growth, drying, or compression. Controlled freezing is one way to produce this effect. As ice crystals grow through a wet gel, they push solid material into the spaces between them. If the crystals grow mainly in one direction, the remaining framework develops parallel walls or channels. Once the ice is removed, the material keeps that alignment. These channels can help liquids travel through the aerogel. They can also improve strength along the direction of the walls. The same structure may be less effective when force is applied across them. Whether this is a problem depends on the intended use. A material designed for one predictable direction of pressure may benefit from alignment. A material expected to face loads from every direction may need a more balanced network. Random structures have their own advantages. They can distribute force through many possible paths. If one connection fails, another may carry some of the load. The network does not depend on a single straight route. This idea of multiple paths appears in electrical behaviour as well. For a graphene aerogel to conduct electricity, the carbon sheets must form a connected route from one side of the sample to the other. A single gap can interrupt one path, but other paths may remain available. The more connected the network becomes, the more reliably current can travel. There is a point during gel formation when separated particles or sheets first create a continuous path across the material. Before that point, the pieces may be individually conductive, but the entire sample is not. After enough connections form, the network begins to behave as one electrical structure. Adding more graphene generally creates more contacts and can improve conductivity. It also increases density. Once again, the design becomes a compromise. A very sparse aerogel may be extremely light but contain too few reliable pathways. A denser one may conduct better and survive handling, but lose some of the quality that made it unusual in the first place. The contacts between sheets are not all equal. Two sheets pressed flat against each other can exchange electrical charge more easily than two sheets touching only at their edges. Chemical bonds can create strong connections. Weak attraction can create contacts that separate when the material moves. Compression often changes these contacts. As the pores collapse, more sheets touch. Electrical resistance may fall. When the material expands again, some contacts disappear and the resistance rises. A sensor can use this change to detect pressure. The same basic event happens throughout the network. A finger presses on the surface. The force travels through walls and junctions. Pores deform, sheets meet. Electrical paths change. The signal measured at the edge of the material becomes a record of what happened inside. For a useful sensor, the response must be predictable. The same amount of pressure should produce roughly the same signal each time. The material should recover quickly. It should not become permanently compressed after a few uses. Temperature and humidity should not create confusing changes. These requirements are much harder to meet than simply proving that resistance changes under pressure. Laboratory demonstrations can show that a material is sensitive. Practical devices must also show stability, repeatability, durability, and a way to connect the delicate aerogel to ordinary wires. The internal architecture affects heat in a different but equally important way. Heat moving through the solid framework must follow the narrow branches and sheets. These paths are longer and more complicated than a straight path through a dense block. Every bend and contact can slow the transfer. In silica aerogel, the solid network carries relatively little heat because there is so little of it. The gas inside the pores also carries little heat because the spaces are small. Gas molecules cannot travel far before meeting a wall. They repeatedly collide with the internal structure, limiting the distance over which they can transfer energy. Larger pores can allow more gas movement. If the spaces become large enough, circulation may begin and insulation performance can fall. Very small pores help suppress this motion, but they may also make it harder for liquids to move through the material. The ideal pore size depends on what the aerogel is meant to do. An insulation panel benefits from pores that restrict heat transfer. An electrode benefits from channels that allow charged particles to move quickly. An absorbent needs open routes that let liquid enter. A filter may need pores small enough to trap certain particles while allowing the rest of the fluid through. One aerogel cannot perform every task equally well. The architecture must be matched to the job. A material with the lowest possible density may not have the best thermal insulation. A material with the greatest surface area may transport liquids too slowly. A highly conductive network may require more carbon and therefore more weight. Surface area is another result of the internal design. A large solid block has most of its atoms buried inside, away from contact with the outside world. In an aerogel, much of the solid exists as thin walls and small branches. A far larger fraction is exposed to the pores. This gives gases and liquids many places to attach. It also allows catalysts to be spread throughout the material. A catalyst helps a chemical reaction proceed without being consumed in the same way as the reactants. The useful part of a catalyst must be accessible. Bury it inside a dense block, and many active sites cannot be reached. Spread it over an aerogel and the available area increases. The aerogel can act as a support, holding tiny catalyst particles apart and preventing them from gathering into larger clumps. This can reduce the amount of expensive material needed. Metals used in catalytic systems can be effective in very small quantities when they are distributed across a large internal surface. The same strategy appears in energy storage. An electrode works best when charged particles can reach a large active area and electrons can move through a connected conductive network. Graphene aerogel offers both possibilities. Its pores provide access, while its carbon framework carries electrical charge. Yet the two routes must be balanced. Electrons travel through the solid. Charged particles move through liquid in the pores. A region that is excellent for one but inaccessible to the other contributes little. The most useful part of the electrode is where both can arrive. Tiny pores provide more surface, but movement through them can be slow. Larger pores act like roads, bringing liquid deeper into the structure. Medium-sized pores connect the roads to the smaller spaces. Many successful designs use this combination of scales. This arrangement is sometimes called hierarchical porosity. The word sounds complicated, but the idea is familiar. A city contains motorways, ordinary streets, and narrow paths. Motorways move people quickly over long distances. Streets distribute them through neighborhoods. Paths lead to individual buildings. An aerogel with several pore sizes can work in the same way. Large channels allow rapid entry. Smaller channels distribute material. The smallest pores provide the greatest surface area. If the system contains only narrow paths, movement becomes slow. If it contains only large roads, much of the useful surface disappears. Creating this hierarchy requires control during manufacturing. Ice crystals can shape large channels. Particles can create smaller pores. Chemical reactions can form tiny gaps within the walls themselves. Templates can produce regular openings. Additives can prevent sheets from stacking too closely. Stacking is a constant concern in graphene-based structures. Flat sheets naturally attract one another. When they come together face to face, they can form dense layers. The space between them becomes inaccessible. Surface area falls, pores disappear, and the material becomes heavier for its size. Wrinkles help prevent perfect stacking. A crumpled sheet cannot lie completely flat against its neighbor. Small folds create gaps. Nanotubes, particles, or polymer chains can also act as spacers, holding sheets apart. These added materials may strengthen the network or give it new functions. Metal oxide particles can store charge. Magnetic particles can allow the aerogel to respond to a magnetic field. Polymers can improve flexibility. Fibers can stop cracks from spreading. Every addition changes more than one property. A polymer may increase strength but reduce heat resistance. A metal particle may improve energy storage but add weight. A water-repelling treatment may protect the material from moisture but reduce its ability to interact with certain liquids. Material design therefore becomes an exercise in choosing which compromises are acceptable. The lighter sample is not always the best sample. The strongest is not always the most conductive. The greatest surface area is not always the easiest to use. Defects also shape the outcome. In ordinary conversation, a defect sounds like a mistake that should be removed. At very small scales, defects can sometimes be useful. A missing atom or damaged bond can create a site where a molecule attaches. An opening in a graphene sheet can allow ions to pass through. Oxygen-containing groups can help a sheet interact with water or bind to another material. Too many defects weaken the carbon network and reduce conductivity. Too few may make the sheets difficult to process. The goal is often not perfection, but controlled imperfection. This is true of many natural materials. Bone contains pores, boundaries, and several different levels of structure. Wood contains fibers and channels. Shells combine hard minerals with softer materials. Their strength comes from organized complexity rather than perfect uniformity. Aerogels often borrow from this approach. Researchers design layered networks, reinforced walls, repeating cells, and structures that change gradually from one region to another. A hard outer surface may protect a softer porous interior. One side may repel water while the other attracts it. A dense region may carry load, while a lighter region provides insulation. The boundary between the aerogel and another material is often as important as the aerogel itself. A sample may perform well on its own, but fail when attached to a metal contact, fabric, wall, or pipe. Differences in expansion can create stress during heating. Adhesives can fill the pores and add unwanted weight. Cutting can damage the surface. For this reason, aerogels are frequently built directly into a larger structure. Silica aerogel can form around fibers. Graphene material can grow on a foam. A wet gel can be cast onto a fabric. The connection develops during manufacturing instead of being added afterward. Fibers are especially useful for brittle aerogels. They act like reinforcement inside concrete. The aerogel supplies insulation, while the fibers carry tension and stop cracks from spreading. The result is heavier than a pure aerogel block but much easier to handle. A practical material must survive vibration, bending, temperature changes, moisture, dust, and repeated contact. It must be cut into useful shapes and installed by people who do not have time to treat every piece like a museum object. The structure must also survive its own production. During drying, different regions may shrink at different rates. Thin branches can pull away from thicker ones. The outside can dry before the center. Residual stress remains trapped inside the finished object. A sample may look intact and still contain weaknesses. A small impact can release those stresses and create a crack. Aging, reinforcement, slower solvent exchange, and controlled drying all help reduce the problem. Density changes across the sample can be equally troublesome. If one region contains more solid material, it may be stronger and more conductive. A lighter region may deform first. In an electrode, this produces uneven current. In insulation, it creates paths where heat moves more easily. Uniformity becomes harder as the object grows. A small sample can be carefully controlled. A large panel contains greater distances, larger temperature differences, and more opportunities for bubbles or contamination. Industrial manufacturing must produce the same architecture repeatedly, not merely once. This need for consistency explains why researchers study aerogel structure so closely. A photograph of the finished block cannot reveal enough. They examine the pores with microscopes, measure how gas moves through them, Test how much surface is available, compress the material, heat it, and track changes in electrical behaviour. Each test reveals a different part of the architecture. A microscope shows shape, a mechanical test shows how forces travel. A conductivity measurement reveals connected paths. An absorption test shows whether liquids can enter. A thermal test shows how energy moves. The results can then be connected to the preparation method. A faster freeze may create smaller channels. More graphene may improve conductivity. A stronger chemical link may improve recovery after compression. A different drying route may preserve finer pores. Over time, the process becomes less like making a mysterious cloud and more like designing a building. The walls, supports, openings, and connections are chosen for a purpose. They are simply built at a scale where no human hand can place them individually. The architecture of Aerogel is unusual because absence performs so much of the work. The pores reduce weight, they slow heat, they hold liquids, they expose surfaces, they allow the solid framework to bend and compress. The empty regions are not unused spaces. They are active parts of the design. Change their size and the material changes. Close them, and conductivity may improve while surface area falls. Open them, and liquids may move more easily while strength decreases. A graphene aerogel is therefore not remarkable only because it contains graphene. It is remarkable because thin carbon sheets have been arranged into a connected three-dimensional system. The system can carry force, charge, heat, and fluids through different routes at the same time. Some routes are straight, others are interrupted, some pores are open, others are difficult to reach. Some walls fold and recover, others crack. The finished behaviour comes from the average result of all these local events. That complexity helps explain why two samples made from similar ingredients can behave differently. One may rebound after being squeezed, another may remain flattened, one may absorb oil quickly, another may conduct electricity more effectively. One may survive high temperatures, another may depend on a polymer that softens. The name on the label gives only the beginning of the description. To understand the material, we must know how its internal city was built. With that structure now in view, the extreme lightness of aerographene becomes easier to explain. It is not simply a small amount of carbon spread randomly through space. It is a network that keeps enough connections to remain whole while removing nearly everything that does not contribute to the framework. The next question is how far that approach can be pushed. How little solid matter can remain before the structure collapses? How can sheets-only atoms thick support a visible object? How can something lighter than many ordinary foams remain useful after being pressed, heated, or filled with liquid? Those questions lead directly into the record-breaking world of aerographene, where the race to reduce density becomes a careful contest between weight, strength, conductivity, and the ability to survive outside the laboratory. The architecture inside the material explains how aerographene can occupy a visible amount of space while containing almost no solid matter. Thin carbon sheets form the walls. Narrow fibres or folded sections act as supports. Large openings fill most of the volume. The finished object is solid because the carbon framework remains connected from one side to the other, but its density can be lower than that of almost any familiar solid. This is where the phrase lighter than air begins to appear. It sounds impossible because we expect a solid to fall through a gas. A stone falls through air. A feather falls more slowly, but it still reaches the floor. Even the lightest plastic foam normally has a greater average density than the atmosphere around it. Some forms of aerographene have been produced with a measured density of about 0.16 milligrams per cubic centimetre. Air near sea level has a density of roughly 1.2 milligrams per cubic centimetre, although the exact value changes with temperature, pressure and humidity. This means that the measured density of the ultralight carbon framework can be around 1/8 of the density of the surrounding air. That statement needs careful handling. It does not mean that a piece of aerographene will behave like a helium balloon and rise toward the ceiling. Most aerographene has open pores. Air enters those pores and becomes part of the sample as it sits in the atmosphere. The material does not seal a large volume of a low-density gas away from the heavier air outside it. A balloon floats because its outer skin encloses a gas that weighs less than the air displaced by the entire balloon. The surrounding atmosphere pushes upward with a buoyant force. If that upward force is greater than the total weight of the skin, the string, and the enclosed gas, the balloon rises. An open aerogel works differently. Air passes through the structure and fills its spaces. Only the fine carbon skeleton displaces a meaningful amount of surrounding air. Since that skeleton occupies a very small fraction of the total visible volume, the buoyant force is not enough to lift the whole object in the simple way suggested by its bulk density. A sample can still appear to float in photographs. It may rest on a flower, a blade of grass, a piece of cotton, or the fine hairs of a plant. It may cling to paper through static electricity. A faint air current may move it. These demonstrations reveal how little the sample weighs, but they do not show ordinary free flight. This distinction does not make the material less impressive. A block large enough to see clearly can weigh only a few milligrams. A piece may be supported by the delicate centre of a flower without bending it noticeably. If placed beside a similar-sized piece of foam, charcoal, or plastic, the difference can be surprising. The low density begins with graphene, but the name Aerographene can create another misunderstanding. A single sheet of graphene is only one atom thick. It is not a foam, and it does not have a useful three-dimensional volume. It is more like an extremely thin carbon membrane. To create aerographene, many carbon-based sheets must be connected into a larger framework. Some materials called graphene aerogels contain sheets made from reduced graphene oxide. Others combine those sheets with carbon nanotubes, polymers, or additional particles. The precise recipe affects the density, flexibility, conductivity, and strength. One famous ultralight carbon aerogel combined large graphene-based sheets with carbon nanotubes. The sheets acted like walls, while the nanotubes helped support and reinforce the structure. This arrangement can be compared with a large building that uses broad panels together with narrow beams. The panels enclose space and distribute loads. The beams stop them from folding too easily. Neither part works as well alone. Thin walls without support can collapse. Narrow supports without walls may fail to form a stable enclosed network. Together, they can create a large structure from very little material. The carbon sheets inside aerographene are not perfectly flat. They bend, wrinkle, and curve around open cells. These folds are useful. A completely flat sheet can lie against another sheet and stick to it. Where many sheets stack together, the structure becomes denser and loses much of its open volume. Wrinkles keep parts of the sheets apart. They create gaps and prevent complete stacking. They also allow the walls to bend under pressure. When the aerogel is squeezed, the folds can close and the sheets can buckle into the pores. When the pressure is removed, the stored elastic forces may push the structure outward again. This is the source of the claim that aerographene is stronger than it looks. The statement does not mean that a small piece can replace a steel beam. Absolute strength and strength compared with weight are different ideas. A thin paper tube can support more weight than a flat sheet of the same paper. The paper itself has not become stronger. The shape has changed the way force moves through it. Aerographene uses a related principle at a much smaller scale. Its carbon walls are arranged into cells, arches, folds, and connected supports. When force arrives, it is distributed through that framework. Some walls bend, some junctions rotate, some pores collapse. Energy is absorbed through many small movements instead of being concentrated at one point. A dense brittle object may resist movement until it cracks. A resilient aerographene structure can allow controlled deformation. It gives way before the carbon framework breaks completely. This ability to deform is one reason some samples can survive very deep compression. Researchers have produced graphene aerogels that can be pressed until they retain only a small fraction of their original height. Once the load is removed, They expand toward their earlier shape. In carefully designed materials, this recovery can continue through many repeated cycles. The sample does not recover because its empty spaces contain compressed springs. The walls themselves act as the springs. Folded graphene sheets bend. Carbon nanotubes flex. Connected cells collapse in a planned sequence. The structure stores some of the mechanical energy and releases it when the pressure disappears. The exact response depends on how the aerogel was made. A weak network may crumble on the first compression. Sheets may slide together and remain stuck. Junctions may tear. Large cracks may spread across the sample. A stronger design uses stable contacts and a structure that guides deformation away from sudden failure. Some graphene aerogels contain chemical links between neighbouring sheets. These links stop the sheets from separating too easily. Others use reinforcing fibres, nanotubes or polymer chains. Printed microlattices can place material in repeating patterns instead of leaving the cells entirely random. A regular lattice gives researchers more control over how the aerogel collapses. They can adjust the width of the walls, the size of the openings, and the direction of the supports. The result may be heavier than the lightest possible random aerogel, but it can be more reliable. This reveals a continuing tension in the design. Lower density requires less solid carbon. Less carbon means thinner walls and fewer connections. Eventually the framework becomes too weak to keep its shape. Increasing the amount of carbon improves the number of load-carrying paths. It can increase electrical conductivity and make the material easier to handle. It also adds weight and may reduce the open space available for liquids and gases. The lightest record sample is therefore not automatically the most practical version. A laboratory can create a piece that demonstrates the lowest possible density, but an industrial product must survive packaging, transport, cutting, installation, and daily use. It must remain consistent when produced more than once. The phrase "stronger than it looks" is most accurate when it describes resilience and performance relative to mass. Aerographene can be remarkably good at surviving compression compared with its tiny weight. It can absorb mechanical energy through the collapse of its cells. It may recover instead of breaking permanently. That is different from saying it can carry enormous loads. A person could damage many ultralight samples with one careless touch. A sharp object can puncture the thin network. Pulling may be more damaging than pressing, because the structure is often designed to buckle inward rather than resist being torn apart. Compression brings neighbouring walls closer and allows the structure to share the load. Tension pulls the connections away from one another. If the junctions are weak, they separate. The material may therefore be highly compressible, but relatively poor at resisting a strong pull. This difference is familiar in other materials. Concrete handles compression well, but requires steel reinforcement when it must resist tension. Rope performs well when pulled, but provides little support when pushed. A material does not have one simple strength value that applies to every situation. Aerographene must be tested under the type of force it will face. A pressure sensor experiences repeated compression. A vibration absorber experiences rapid movement. An electrode may expand and contract as it takes in charged particles. A filter faces flowing gas. A structural panel may need to survive bending and impact. Each use places different demands on the internal framework. A sample that performs well in one test may fail in another. This is why scientific papers describe compression, recovery, stiffness, fatigue, and energy absorption separately. Stiffness tells us how strongly a material resists changing shape. A very stiff object moves little under load. Aerographene is usually not stiff in the ordinary sense. Its open cells allow substantial movement. That softness can be useful. A pressure sensor must respond to a gentle touch. A stiff block would barely change. A compressible graphene aerogel deforms, bringing sheets into new contact and changing the way electricity travels through the network. The electrical response can then be measured. The light structure also gives it a low mechanical inertia. Inertia is the tendency of matter to resist changes in motion. Since aerographene contains very little mass, it can respond quickly when a force appears or disappears. This may help in sensitive detectors and devices that must follow rapid vibrations. Low mass can also reduce the amount of energy needed to move a component. In aircraft, spacecraft, portable electronics, and wearable equipment, every saved gram can matter. A light sensor places less strain on fabric or skin. A light electrode reduces the portion of a battery that does not directly store energy. Yet the supporting equipment can easily outweigh the aerogel. Wires, protective cases, adhesives, current collectors, and packaging all add mass. A spectacular density record for the active material does not guarantee a spectacular density for the finished device. The aerogel must also connect to ordinary solid components. Attaching a wire to a delicate carbon sponge is not as simple as attaching one to a metal plate. A rigid contact may tear the aerogel when the device bends. An adhesive may fill the pores and block useful surfaces. A coating may increase strength, but also reduce sensitivity. These practical details rarely appear in photographs of a sample balanced on a flower. They become important as soon as the material leaves the research bench. Temperature presents another challenge. Graphene and carbon nanotubes can tolerate a broad range of temperatures when protected from reactions with the surrounding environment. The open structure of aerographene exposes a great deal of carbon surface to the air. At sufficiently high temperatures, carbon can react with oxygen and burn. Tests performed in an inert gas or vacuum can show impressive thermal stability because oxygen has been removed. The same sample may behave differently in ordinary air. Claims about temperature resistance must therefore include the conditions under which the material was tested. At low temperatures, some ultralight carbon aerogels can retain their flexibility. This is valuable because many materials become brittle when chilled. Space equipment, scientific instruments, and energy systems may experience extreme changes in temperature. A network that remains resilient across those changes offers useful possibilities. The empty space inside aerographene also helps it absorb impact energy. When a cellular material is compressed, its walls collapse gradually. The force required may remain relatively steady over a large amount of deformation. This allows the material to take in energy without transmitting all of it immediately to whatever lies behind it. Conventional foams use this principle in helmets, packaging, seating, and protective barriers. Aerographene may provide similar behavior at far lower mass, though its cost and durability remain serious considerations. A protective material must do more than survive one careful laboratory test. It may need to endure moisture, dust, temperature cycling, vibration, and repeated impacts. The aerogel may require a skin or supporting layer. That protection adds weight, but can make the internal structure usable. Strength can also be improved by copying biological materials. Natural structures rarely depend on one uniform network. Bone contains dense outer regions and porous interiors. Plant stems combine stiff fibers with lighter supporting tissue. Shells use layers that redirect cracks. Researchers can give graphene aerogels similar variations. One region may contain larger cells for compression. Another may contain smaller pores for strength. Layers can be arranged in different directions. Fibers can bridge weak boundaries. A gradient in density can prevent stress from concentrating suddenly. Instead of moving from a hard surface directly into a fragile interior, the structure changes gradually. Force spreads across a larger region. Three-dimensional printing offers more direct control. A thick ink containing graphene oxide can be deposited into a planned pattern. The printed object is gelled and dried while its arrangement is preserved. Designers can create repeating beams, open lattices, and shapes that would be difficult to produce through random self-assembly. Printed graphene aerogels are generally denser than the most extreme record holders. Their strength comes from organization rather than from reaching the lowest possible mass. The beams can be placed where calculations suggest they will carry the greatest load. This is the difference between a pile of branches and a bridge. Both may contain the same amount of material, but one has been arranged to guide force along useful routes. Even a random aerographene network contains a form of organisation. The graphene sheets are connected enough to span the sample. Their wrinkles create spring-like behaviour. Nanotubes can cross open gaps. The walls meet at angles that help the cells resist collapse. During compression, the largest and weakest pores often begin closing first. As the sample becomes denser, more walls touch, and further compression becomes harder. The material may therefore feel soft at the beginning and increasingly firm as it is squeezed. This changing resistance can protect the structure from complete collapse. Gentle pressure is absorbed easily. Greater pressure brings more of the framework into contact, allowing it to carry a larger load. When released, the walls separate and the pores reopen. Repeated movement causes fatigue. Tiny cracks form. Contacts wear or shift. Some sheets remain stuck together. The height may recover slightly less after each cycle. Good aerographene design reduces this damage. Strong junctions prevent sheets from pulling apart. Curved walls avoid sharp points where stress concentrates. Reinforcing fibers spread force. A regular cell pattern makes deformation more predictable. Later graphene-based metamaterials have pushed these ideas further by creating extremely light structures that recover after repeated deep compression. Their performance comes not only from graphene, but also from the way the cellular framework has been designed. The word metamaterial refers to a material whose large-scale behavior depends strongly on its designed structure. The ingredients may be ordinary, but the pattern produces an unusual response. In aerographene, thin carbon walls can be arranged so the object bends, springs back, absorbs vibration, or changes its electrical behavior under pressure. This design freedom makes the material more than a competition for the lowest density. A record number may introduce the public to aerographene, but engineers are more interested in controlled performance. A slightly heavier aerogel that works for thousands of compression cycles may be more useful than a lighter one that collapses when removed from its mould. A reinforced sample may lose the right to call itself the lightest, yet gain the ability to become a sensor, an electrode, or an absorbent used more than once. The absorbent behaviour provides another example of strength through structure. Graphene-based aerogels can take in oils and organic liquids throughout their open pores. A sample may absorb many times its own weight, because its own weight is extremely small and its internal volume is large. After absorption, the situation changes. The pores that once held air now contain liquid. The sample becomes much heavier. Its framework must support that added mass without collapsing. A resilient aerogel can sometimes be squeezed to remove part of the liquid and then reused. The walls compress, the liquid is forced out and the structure expands again. This combines absorption with mechanical recovery. The same lightness that makes the dry sample impressive creates a demanding test once it is full. A material that weighs almost nothing may be asked to hold a quantity of liquid hundreds of times greater than its dry mass. Strong connections between sheets become essential. Electrical conduction must survive the same movements. A graphene aerogel may remain conductive while it is compressed, although its resistance usually changes. This allows it to function as both a mechanical structure and an electrical component. Traditional foams often require conductive particles to be added. Aerographene begins with a carbon framework that can already carry charge, provided the sheets are well connected and sufficiently reduced. That combination of low mass, open volume, resilience and conductivity is rare. A metal foam conducts electricity and survives handling, but it is heavier. A polymer foam is light and flexible, but usually does not conduct well. A brittle carbon structure conducts, but may not recover after compression. Aerographene attempts to combine parts of all three. It remains imperfect, and each improvement in one property may weaken another. Still, the combination explains why the material continues to attract attention long after its density record first appeared. It also explains why strength cannot be judged by appearance. The black sample looks like ash, or burnt sponge. Ash falls apart because its particles are poorly connected. Aerographene contains a continuous network. The amount of carbon is tiny, but it has not been scattered randomly. The sheets and fibres meet often enough to form load-carrying paths. They bend rather than immediately separate. The open cells allow movement without requiring every carbon bond to stretch directly. The material survives not by refusing to change shape, but by changing shape in a controlled way. That is a different kind of strength from the rigid strength of a stone or steel bar. It is the strength of a structure that knows where it can bend. There are limits. A record-breaking aerographene sample should not be treated as indestructible. It can be damaged by tearing, abrasion, sharp impacts, uncontrolled heating, or careless handling. Its performance may decrease in humid or chemically aggressive conditions, depending on its surface treatment and added materials. Manufacturing remains difficult. Producing large samples with uniform pores and reliable connections takes time and careful control. Freeze-drying and heat treatment consume energy. Graphene oxide preparation uses chemicals that must be managed safely. The final material can be expensive. Researchers are working on simpler starting materials, faster drying methods, lower temperature processing, and structures that need less reinforcement. They are also exploring biomass-derived carbon, recycled materials, and combinations that reduce the required amount of graphene. The goal is not merely to make the material lighter. The goal is to make its lightness useful. A practical aerographene may eventually sit inside a pressure sensor, an energy storage device, an insulation system, a vibration damper, or equipment designed to collect oil from water. In each case, the surrounding structure will protect it and connect it to the rest of the device. The aerogel itself may no longer be visible. Its record density may matter less than its surface area. Conductivity, recovery, or ability to hold another substance. That is usually what happens when an unusual material becomes useful. It stops appearing only in demonstrations and begins working quietly inside ordinary systems. For now, aerographene remains a clear example of how far material design can separate size from weight. A visible object does not need to be filled with matter. A strong response does not always require a rigid block. Thin walls, careful connections, and large amounts of open space can create a structure that weighs almost nothing and still returns after being pressed nearly flat. Its lightness attracts attention, but its behaviour under pressure reveals the deeper achievement. The carbon framework remains connected while the pores close and reopen. Electricity continues to find paths. Liquids can enter and leave. Mechanical energy can be absorbed across thousands of tiny folds. Those same pathways do more than carry force. They affect heat, sound, electrical charge, light, and the movement of molecules. Once aerographene is viewed as a working network rather than simply a record-breaking solid, its other unusual abilities begin to make sense. Once the internal network is understood, the unusual abilities of Aerogel stop looking like separate tricks. Heat, electricity, force, and sound all have to travel through the same crowded arrangement of pores and thin solid walls. Change that arrangement, and each form of energy behaves differently. This is why two aerogels made from similar ingredients can perform completely different jobs. One can protect an instrument from heat, another can carry electrical charge, a third can absorb vibration, a fourth can do several of these things at once, although usually with some compromise. Heat is a useful place to begin because thermal insulation made aerogel famous long before graphene-based versions began appearing in laboratories. A dense solid gives heat many connected paths. The atoms and molecules are close together, allowing energy to pass from one region to another. Metals are especially good at this. Touch a metal object in a cold room and it quickly carries heat away from your skin, which makes it feel colder than wood or fabric at the same temperature. Aerogel contains far fewer solid pathways. The framework stretches across the material, but it does so through narrow branches, thin walls, and small points of contact. Heat trying to move through the solid part must follow a long and interrupted route. It crosses junctions, passes through bends, and encounters boundaries where energy is scattered. The gas inside the pores also has difficulty carrying heat. In open air, warmer gas can rise while cooler gas falls, creating circulating currents. This movement is called convection, and it is one reason an open room does not remain warm near a heater and cold everywhere else. Inside aerogel, the pores are too small for useful currents to develop. The gas cannot circulate freely. Its molecules move only short distances before meeting the solid walls. Their motion is restricted, so the gas transfers heat less effectively than it would in a larger open space. This is similar to what happens inside thick clothing. A winter coat does not create warmth by itself. It traps air and prevents that air from moving easily. The trapped gas slows the loss of heat from the body. Aerogel follows the same general idea but uses much smaller spaces and much less solid material. The size of those spaces matters. If the pores are too large, the gas can move more easily and carry heat through the structure. If they are very small, collisions with the pore walls become more frequent. This reduces the distance gas molecules can travel while carrying energy. Heat can also move as radiation. Warm objects release energy that can cross empty space. This is how heat from the sun reaches Earth, and how a fire warms your face even when the surrounding air is cold. Some aerogels allow a portion of thermal radiation to pass through. Others contain particles or additives that absorb or scatter it. An insulation material designed for high temperatures may include substances that reduce this radiative transfer. Without them, a very light aerogel can perform well at moderate temperatures but become less effective as radiation begins carrying more of the heat. The best thermal performance therefore comes from controlling several routes at once. The solid framework must remain sparse. The pores must restrict gas movement. The structure may need to block or scatter thermal radiation. It must also remain stable at the temperature where it will be used. Silica aerogel is especially effective as a thermal insulator because silica itself carries heat poorly compared with metals, and the porous structure reduces heat flow even further. A thin layer can provide insulation that would require a much thicker layer of some conventional materials. This does not mean every aerogel is equally good at stopping heat. Carbon-based aerogels behave differently. A single high-quality graphene sheet can conduct heat very well along its surface. The carbon bonds provide an efficient route for energy. Inside aerographene, however, the sheets are folded, separated, and connected imperfectly. Heat moving through the sample cannot travel along one continuous sheet from beginning to end. It must cross wrinkles, edges, contacts, and gaps. Each transition slows the transfer. The overall material can therefore conduct heat much less effectively than an isolated sheet of graphene. The difference shows why the properties of a building block do not automatically become the properties of the larger structure. A steel beam is strong, but a loose pile of steel dust is not a bridge. A copper wire conducts electricity well, but two wires separated by a gap carry no current between them. Graphene may have excellent thermal behavior in one form, and very different behavior when arranged into an open aerogel. This can be useful. Aerographene can absorb light efficiently because its dark carbon surfaces interact with a wide range of wavelengths. When light enters the pores, it may strike several internal surfaces before escaping. Each encounter creates another opportunity for energy to be absorbed. The absorbed energy can become heat. A dark graphene-based aerogel placed in sunlight can warm rapidly, even though the sample contains very little material. The heat may remain concentrated near the illuminated surface because the porous structure does not carry it away quickly. Researchers can use this behavior to heat water, speed evaporation, or create sensors that respond to light. A floating layer of carbon aerogel can absorb sunlight while drawing water toward its warm surface. The surface water evaporates, leaving salts or other material behind. The idea sounds simple, but practical systems must control several problems. The aerogel has to remain stable in water. It must allow liquid to move through its pores. It must avoid becoming blocked by salt or contamination. It must survive repeated heating and drying. Electricity follows a different route. Gas-filled pores do not normally carry current well. The electrical path lies mainly through the solid carbon network. For that path to work, graphene sheets, carbon particles, or nanotubes must touch one another from one side of the material to the other. A silica aerogel is usually a poor electrical conductor. Its structure can insulate against electrical current just as it insulates against heat. This is useful when the material must protect equipment without creating unwanted electrical connections. Carbon aerogels can conduct because carbon provides pathways for moving charge. The level of conductivity depends on how the carbon is arranged. A dense network with many contacts usually carries current more easily than a very sparse one. Reduction and heat treatment can improve the conductivity of graphene aerogel. Graphene oxide contains oxygen groups that interrupt the carbon network. Removing many of those groups restores longer paths through which electrons can move. The removal is rarely perfect. Defects remain. Sheets meet at awkward angles. Some contacts are weak. The finished aerogel therefore does not conduct as well as a perfect graphene sheet, but it can conduct well enough for sensors, electrodes, heaters, and other devices. The pores that reduce weight also create an advantage. They give liquids and gases access to the conductive surface. In a dense piece of carbon, most of the atoms remain buried. In an aerogel, a large portion of the carbon sits beside open space. This is important in energy storage. A battery or capacitor depends on the movement of electrical charge and charged particles. Electrons travel through the solid electrode. Charged particles move through a liquid or solid electrolyte. Useful storage occurs where these routes meet. Graphene aerogel can provide a connected path for electrons, while its pores allow the electrolyte to enter. The internal surface offers many places where charge can gather or chemical reactions can occur. Very small pores increase the available area, but they can slow the movement of charged particles. Larger channels allow faster transport but provide less surface. A successful electrode often needs both. Large pores act as entrances. Medium-sized passages distribute the liquid. Small pores provide active surface. The different scales work together, much like main roads, local streets, and paths leading to individual houses. Electrical performance changes when the aerogel is compressed. As the pores close, more carbon sheets touch. New paths appear and the resistance can fall. When the pressure is removed, some contacts separate and the resistance rises again. This change turns the material into a sensor. A small force applied to the surface creates a measurable electrical response. The greater the pressure, the more the structure changes. A sensor of this kind can detect a finger tap, movement in a joint, vibration from a machine, or pressure beneath a soft surface. Because the aerogel weighs very little, it can be added to clothing or flexible equipment without creating much extra load. Sensitivity alone is not enough. The signal must remain stable. The material must return to the same state after each use. If the sheets slowly stick together, the resistance may drift. If cracks form, electrical paths may disappear permanently. Temperature can also alter conductivity. Moisture may enter the pores and change the contacts. Oils from skin can coat the surface. A useful sensor requires protection, calibration, and a design that separates the desired signal from all the unwanted changes. Aerographene can also act as a very light electrical heater. When current passes through a resistive material, some electrical energy becomes heat. A thin carbon network can warm quickly because it has little mass. Rapid heating can be useful in desing, wearable warmth, or temperature control. The structure may also cool quickly once the current stops. This allows a device to respond without waiting for a heavy component to change temperature. The same low mass creates a risk. A small amount of energy can raise the temperature rapidly. If current concentrates in one weak region, that area may overheat. The aerogel needs uniform contacts and careful control to avoid damage. Mechanical behavior adds another group of unusual effects. Some aerogels are rigid and brittle, others are flexible and springy. The difference comes from the material in the framework and from the way the pores collapse. Silica aerogel often resists small forces without much movement, then cracks once the stress becomes too large. Graphene aerogel can bend because its walls are thin sheets. The sheets wrinkle, fold and slide before the carbon bonds themselves break. When the material is compressed, the largest and weakest pores close first. The sample may feel soft at the beginning. As more pores collapse and more walls contact one another, it becomes harder to squeeze. This gradual increase in resistance allows the aerogel to absorb mechanical energy. Instead of sending the entire force straight through, it uses that force to bend walls and close pores. Conventional foams use the same general principle in packaging and protective equipment. Aerographene can achieve similar behavior with far less mass. It may also remain electrically active while deforming, which allows one object to absorb force and measure that force at the same time. Repeated compression tests reveal how well the structure survives. A good sample returns close to its original height after the load is removed. The electrical response also returns close to its earlier value. Over many cycles, some permanent change is expected. Junctions weaken, sheets rub against one another, tiny cracks appear. The sample may become slightly shorter or softer. Reinforcement can reduce this fatigue. Carbon nanotubes can bridge gaps. Polymers can hold sheets together. Carefully designed cells can guide the collapse. Thicker walls can survive longer, although they add mass. The strength of aerographene is therefore not the rigid strength of a heavy block. It is a controlled ability to bend, compress and recover. It survives by allowing movement. This makes the material useful in vibration control. A vibration is repeated motion carrying energy through a structure. Machines, vehicles, buildings and electronic equipment all experience it. A porous network can absorb some of that energy as its walls flex. Friction between sheets converts part of the motion into heat. The heat produced is tiny and spreads through the structure, but the original vibration becomes weaker. Different pore sizes respond to different frequencies of motion. A soft, open network may handle slow movement well. A denser structure may interact more strongly with rapid vibration. Designers can adjust the stiffness and arrangement to target a particular range. Sound is also a vibration. In air, it travels as changing pressure. A speaker pushes the surrounding air, creating regions of compression and expansion. These pressure changes move outward until they reach the ear or another surface. When sound enters a porous material, the moving air is forced through narrow passages. It rubs against the internal walls. Some of the organized motion becomes heat. The complicated route also scatters the sound, reducing the amount that passes straight through or reflects back. This is why soft fibrous materials can make a room quieter. Curtains, carpets, upholstered furniture, and acoustic panels all contain spaces that interfere with moving air. Aerogels can do something similar, but their pore sizes and solid content are very different. The word silence in connection with aerogel should not be taken too literally. A small block will not erase every sound around it. Acoustic performance depends on thickness, pore structure, stiffness, and the frequency of the sound. Low-frequency sound is particularly difficult to block. Its long waves pass through thin materials easily. Reducing it often requires heavy barriers, large airspaces, or specially designed structures. Aerogels are light, which can limit their ability to stop sound by mass alone. A heavy wall resists movement and reflects sound. An ultralight material cannot rely on that strategy. Instead, it can absorb or scatter sound within its pores. Some aerogels are combined with fibers, layers, or cavities to improve performance. A dense skin may reflect part of the sound, while the porous interior absorbs another part. The result can be a material that provides thermal and acoustic insulation at the same time. This is attractive in aircraft, vehicles, buildings, and equipment where space and weight are limited. An ordinary wall may need one layer for heat, another for noise, another for fire resistance, and another for strength. A carefully designed aerogel composite could perform several of these functions within a thinner structure. Combining functions is difficult because the best structure for heat may not be the best one for sound. Tiny pores restrict gas movement and improve thermal insulation. Larger connected pores may absorb certain sound frequencies more effectively. A rigid structure can reflect sound but may crack. A soft structure can absorb vibration but may conduct heat differently. Engineers adjust density, thickness, pore size, and supporting layers to find a useful balance. The surface of the aerogel can also influence sound. A sealed surface prevents air from entering the pores, reducing absorption. An open surface allows better interaction, but may release dust or absorb moisture. Protective coverings must therefore be chosen carefully. A fabric can hold the material together while allowing sound and air to pass. A solid film may improve durability but reduce acoustic performance. Fire behavior creates another challenge. Silica aerogel does not burn easily because silica is already a stable oxide. It can tolerate high temperatures, although its structure may change or shrink under extreme conditions. Graphene aerogel is made from carbon and can burn in the presence of oxygen if it becomes hot enough. The open pores expose a large surface to the air, which may allow the reaction to spread quickly once it begins. Fire-resistant coatings, mineral additives, or protective layers can improve safety. These additions may also change weight, flexibility, and electrical behavior. The ability to absorb light can make heating faster, which is useful in some devices and dangerous in others. A black carbon aerogel placed near intense radiation may become hot even when the surrounding air remains cool. Every unusual ability therefore arrives with a condition. Aerogel slows heat, but not under every temperature and pressure. Aerographene conducts electricity, but only when enough pathways remain connected. It recovers after compression, but repeated cycles cause fatigue. It reduces sound, but performance depends strongly on thickness and frequency. The material is not powerful because it ignores physical laws. It is powerful because its structure guides those laws in useful ways. Heat is forced through narrow routes. Electricity follows connected carbon walls. Mechanical force closes pores and bends sheets. Sound loses energy while pushing air through a complicated internal maze. One structure manages several kinds of movement. That is the real source of the strange behavior. Scientists can modify the network depending on which movement matters most. Smaller pores for insulation, better carbon contacts for conductivity, curved walls for recovery, fibrous reinforcement for sound and vibration. They can add particles that absorb radiation, chemicals that react with pollutants, metals that store electrical charge, or polymers that prevent cracks. The aerogel becomes a platform rather than one finished product. This flexibility is why so many possible uses have been proposed. A material that is light, porous, conductive, compressible and absorbent can fit into many kinds of device. It can sit between hot and cold surfaces. It can become an electrode. It can detect pressure. It can hold a catalyst. It can collect oil. The difficulty lies in deciding which property matters most. Improving one can weaken another. Adding carbon improves conductivity but increases density. Adding polymer improves strength but may reduce heat resistance. Closing pores protects the interior but blocks liquids and sound. A practical design accepts these trade-offs. It does not chase the highest result in every test. It chooses a combination that survives real conditions. This is where aerogel begins to move beyond laboratory demonstrations. The flame above a flower proves that heat transfer can be slowed. The compressed black sponge proves that a carbon network can recover. The changing electrical signal proves that pressure can be detected. The next step is placing those abilities inside equipment that has to work for months or years. Spacecraft must survive launch vibration and extreme temperature changes. Industrial insulation must tolerate dust, moisture, and careless handling. Spill cleanup materials must absorb large amounts of liquid and then be collected safely. Once the strange powers of the material are matched to these ordinary demands, Aerogel stops being only an object of curiosity. It becomes part of a spacecraft, a pipeline, a battery, a sensor, or a cleanup system, working quietly where low weight and large internal space are worth the effort required to make them. A material can perform beautifully in a laboratory and still remain little more than a scientific curiosity. The real test begins when it has to leave the clean bench, enter a machine, survive careless handling, and continue working after the first impressive demonstration is over. Aerogel has crossed that boundary in several important ways. Some uses are already established, others remain experimental. Together they show how a material built mostly from empty space can become useful in places where ordinary solids are too heavy, too thick, or too willing to carry heat. Space exploration gave Aerogel one of its earliest practical homes. The reason is simple. Spacecraft must survive large changes in temperature while carrying as little unnecessary mass as possible. Every added kilogram demands more fuel, more structural support, and more expense. Engineers therefore value insulation that can slow heat without requiring a thick and heavy layer. Mars is a particularly difficult place for electronic equipment. The atmosphere is thin, sunlight can warm exposed surfaces during the day, and temperatures fall sharply after sunset. A rover may spend the daylight hours moving, drilling, photographing, and examining rocks, then face a long, cold night with its instruments and batteries protected inside the body. Silica aerogel was used to insulate the small Sojourner rover carried by the Mars Pathfinder mission. The aerogel sat around sensitive equipment and reduced the rate at which heat escaped. It did not make the rover warm by itself. It helped preserve heat that was already present, allowing heaters and stored energy to work more effectively. The same general approach continued in later Mars rovers. Aerogel insulation became valuable because it offered strong thermal protection without taking up the space required by thicker conventional insulation. Inside a rover, every small area is already claimed by wires, computers, instruments, batteries, supports, and mechanisms. There is rarely a spare cupboard where engineers can place an extra blanket. The job may sound quiet, but quiet jobs are often the ones that keep a mission alive. A camera receives attention when it sends home a remarkable image. A drill receives attention when it reaches an interesting rock. Insulation receives attention mainly when it fails. Aerogel has spent much of its working life being successful enough to remain unnoticed. A different space mission used aerogel not to stop heat, but to stop dust. The Stardust spacecraft travelled to the comet Wild 2 and carried panels filled with low-density silica aerogel. The purpose of those panels was to capture tiny particles moving at very high speed. Catching a comet particle is not like catching dust on a shelf. A fast particle carries enough energy to break apart, melt, or vaporize when it strikes a hard surface. Scientists wanted to bring material back to Earth with as much of its original structure and chemistry preserved as possible. Aerogel offered a gentle form of braking. When a particle entered the porous material, it did not meet one solid wall. It passed through a long sequence of fine branches and gas-filled spaces. The resistance increased gradually, slowing the particle across a short track. Each captured object left a narrow trail that widened near the entrance. The tracks often looked like tiny carrots pressed into the transparent material. At the end of a track, scientists could find fragments or entire particles that had travelled from a comet. The collector returned to Earth in a capsule that landed in Utah in 2006. More than 10,000 particles larger than 1 micrometer were brought back from Wild 2. Researchers removed small sections of aerogel around individual tracks and studied the material inside them. The aerogel was not perfectly invisible during capture. Some of it melted or reacted near the fastest particles. Scientists had to separate changes caused by the impact from the original features of the comet dust. Even with that complication, the mission achieved something that a hard metal plate could not. It brought fragile extraterrestrial material home for direct examination. The same ability has made aerogel useful in experiments involving cosmic dust and high-speed particles. A low-density collector can slow material while preserving a visible record of its path. The shape of that path reveals information about the impact, and the particle at the end provides a sample for analysis. Aerogel also appears in the less glamorous but essential problem of storing very cold fluids. Rockets use propellants that may have to remain at cryogenic temperatures. Heat entering a tank causes part of the liquid to boil. If the gas cannot be managed, pressure rises. If the gas must be released, valuable propellant is lost. This problem becomes more serious during long missions. A launch vehicle may use its fuel soon after filling, but a spacecraft travelling toward the Moon or Mars may need to store cryogenic liquids for weeks or months. Even a small continuous heat leak becomes important over that length of time. Aerogel-based blankets, particles, and layered insulation systems have been tested for tanks and transfer lines. Their tiny pores restrict gas conduction, and their low density limits added mass. Some systems combine aerogel with reflective layers that reduce thermal radiation. Each part handles a different route by which heat tries to enter. The insulation must survive vibration during launch, changes in pressure, repeated cooling and warming, and contact with moisture before flight. A perfect laboratory sample is not enough. It must be turned into a blanket, coating, or composite that technicians can install around curved pipes and complicated joints. Joints are often where insulation systems struggle. A large smooth tank can be covered carefully, but valves, supports, pipes, and electrical connections create paths for heat. Aerogel is useful partly because flexible blankets can wrap around shapes that are difficult to protect with rigid foam. NASA has also studied reinforced aerogel for flexible thermal protection systems used on inflatable devices that help spacecraft slow during atmospheric entry. These structures must be packed for launch, deployed in flight, and exposed to intense heating. The insulation needs to be light, flexible, and stable, while the outer layers face the hot flow of gas. Other proposed space uses go even further. Researchers have investigated aerogel layers for future habitats and greenhouses on Mars. A translucent silica aerogel panel can allow visible sunlight through while slowing heat loss and blocking much of the harmful ultraviolet radiation. In experiments designed to imitate Martian sunlight, a thin layer produced substantial warming beneath it. That does not mean Martian towns are ready to be assembled from frozen smoke. A real habitat must manage air pressure, radiation, dust, structural loads, repairs, and contamination. Aerogel would be one part of a much larger system. The research shows that the material may create warm local regions without heating the entire planet, which is a more manageable goal than trying to give Mars a pleasant climate before lunch. Back on Earth, aerogel found a practical role in industrial insulation. Pipes carrying hot liquids lose energy to their surroundings. Pipes carrying very cold liquids gain heat from the air around them. Both problems waste energy and can interfere with safe operation. Silica aerogel blankets can be wrapped around pipes, tanks, processing equipment, and vessels. The fibers in the blanket give strength, while aerogel fills the spaces around them and limits heat transfer. The material can provide useful insulation in a thinner layer than many traditional products. Thickness matters in crowded industrial facilities. Pipes may run close together. Equipment may sit near walls or walkways. Adding several centimeters of insulation can obstruct access or require expensive changes to the surrounding structure. A thinner blanket can fit where a bulky layer cannot. Aerogel insulation is also used in systems involving liquefied natural gas and other cold industrial fluids. At low temperatures, ordinary insulation can suffer from moisture, cracking, or changes in performance. Aerogel composites can be designed to repel liquid water while allowing water vapor to pass, reducing some of the problems caused by trapped moisture. Installation still requires care. Cutting blankets can release fine dust. Workers may need gloves, protective clothing, eye protection, and masks. Seams must be closed properly. Compression can change performance. A damaged outer covering can allow water or chemicals to reach the insulation. Cost remains one of the main barriers. Aerogel materials are more expensive than common mineral wool or foam. They make the most sense where space, weight, temperature range, or energy savings justify the additional price. In a simple wall with plenty of room, ordinary insulation may remain the sensible choice. Around a complex hot pipe in a crowded plant, aerogel may earn its keep. Buildings offer a similar mixture of opportunity and difficulty. Aerogel blankets can improve insulation in thin walls, roofs, and historic structures where increasing thickness is not practical. Granules can be placed inside panels. Translucent aerogel can fill the space between sheets of glass or plastic, allowing daylight to enter while reducing heat transfer. A normal window is a weak point in an insulated building. Clear glass allows light through, but also loses heat more readily than a well-insulated wall. Aerogel offers a way to create a panel that admits diffuse daylight while restricting heat flow. The view through such a panel is usually cloudy rather than clear. It may work well in a roof light, bathroom, stairwell, or office area, where daylight matters more than seeing the exact expression of the neighbour across the street. Researchers continue to develop transparent and flexible aerogels for window retrofits. The goal is to improve insulation without replacing the entire window. Manufacturing cost, optical clarity, durability, and installation remain difficult. The idea is promising precisely because windows occupy such a large area in many buildings and quietly exchange heat with the outdoors all day. Aerogel has also entered clothing and outdoor equipment through composite insulation. Pure aerogel is too fragile and dusty to place loose inside a jacket. When incorporated into fibres or supported within flexible layers, it can reduce heat loss in gloves, boots, sleeping bags, and protective garments. The advantage is most noticeable where insulation must remain thin. A thick mitten may keep a hand warm but make it difficult to use tools. A bulky boot may protect against cold but become tiring to wear. Aerogel-based inserts can add thermal resistance without requiring as much volume. The material does not remove the need for ordinary fabric. Clothing must bend, breathe, survive washing, and remain comfortable against the body. Aerogel works as one ingredient inside a layered design. It is the quiet passenger rather than the entire vehicle. Graphene aerogel is moving into a different set of applications because it can conduct electricity. Many of these uses remain at the research or early development stage. They are not yet as established as silica aerogel insulation, but they show why a light carbon network attracts so much attention. Energy storage is one major area. An electrode needs electrical pathways and a large surface where charged particles can interact. Graphene aerogel provides a connected carbon framework with liquid-filled pores running through it. Electrons can move through the solid walls while charged particles move through the surrounding electrolyte. Researchers have used graphene aerogels in supercapacitors and battery electrodes. Supercapacitors store charge at surfaces and can deliver energy quickly. The large internal area of an aerogel gives them many places to store that charge. The difficulty is turning laboratory performance into a compact, durable device. A very light electrode may occupy too much volume. Thick electrodes may develop slow regions that charged particles cannot reach quickly. The aerogel must be attached to current collectors, filled with electrolyte, sealed and produced consistently. Graphene sheets also tend to stack together, reducing the accessible surface. Three-dimensional networks help keep them apart, but the network must be compressed enough to fit inside a practical device. Too much compression closes the pores, too little wastes space. Pressure sensors make use of the same structure in another way. When graphene aerogel is squeezed, its sheets move closer and create new electrical contacts. The resistance changes. A circuit measures that change and turns it into a pressure reading. Recent research has produced flexible graphene aerogel sensors capable of detecting small physiological signals and surviving many repeated loading cycles. Such materials could be placed in wearable devices, robotic grippers, soft control surfaces, or medical monitoring equipment. A sensor attached near the throat could detect movement during speech. One placed beneath a foot could map pressure while walking. A robotic hand could use a soft sensor to notice when it has grasped a fragile object firmly enough without crushing it. These examples are still developing. Real devices must deal with sweat, temperature, bending, aging, electrical noise, and the need for simple manufacturing. A remarkable sensitivity measured in a laboratory does not automatically produce a reliable product. The aerogel has to become part of a complete system. The large internal surface of graphene and carbon aerogels can also support catalysts. Tiny metal particles can be distributed across the framework rather than gathering into large clumps. Gases or liquids enter through the pores and meet the active surfaces. This approach is studied for fuel cells, chemical production, pollution control, and reactions that split or combine molecules. The aerogel acts as a scaffold. It holds the active material where fluids and electrical charge can reach it. Filters and purification systems use the pores in a related way. Aerogels can be modified to attract dyes, metals, organic chemicals, or gases. A contaminated fluid passes through the structure, and unwanted molecules attach to the internal surfaces. The challenge is selectivity. A material that absorbs everything soon fills with harmless substances and leaves the dangerous ones behind. Useful filters need surfaces designed for particular pollutants. They must also release or safely contain what they capture. Oil cleanup is one of the most visually convincing applications for graphene-based aerogels. Many carbon surfaces repel water while attracting oils and organic liquids. Place a suitable aerogel on an oil-covered surface, and the oil enters the pores while much of the water remains outside. Because the dry aerogel weighs so little and contains so much open volume, it can take in many times its own mass. Some laboratory studies have reported absorption greater than 100 times the mass of the carbon material, depending on the liquid and the structure. This comparison sounds almost magical until the starting weight is remembered. A sponge that weighs very little does not need a huge amount of oil to exceed its own mass many times. The more important questions are how quickly it absorbs, whether it selects oil over water, and whether it can be collected and reused. A resilient graphene aerogel can be squeezed to remove part of the oil. It may then expand and absorb again. Other recovery methods use heating, pumping, or solvents. Each method has costs. Squeezing requires equipment. Heating requires energy and may release vapors. Solvents create another liquid that must be handled. Oil viscosity also matters. A light fuel moves into pores more easily than heavy crude oil. Cold oil can become thick and slow. Researchers have explored using the dark carbon framework as a heater. Sunlight or electrical current warms the aerogel and the nearby oil, reducing its viscosity so it can enter and leave more easily. Magnetic particles can be added so the oil-filled aerogel can be guided or collected with a magnetic field. Reinforcing sponges can improve durability. Surface treatments can increase water repellence. Every improvement adds material and processing. A magnetic, reinforced, electrically heated graphene aerogel is no longer the simplest or lightest version. It may still be useful if the added functions solve the practical problems of a real spill. A large marine spill is a demanding environment. Waves tear fragile materials. Wind scatters light pieces. Salt, sand, plants, and debris block pores. The absorbent must be spread across a wide area and then recovered before it becomes another form of pollution. Producing enough graphene aerogel for that task would require inexpensive raw materials, rapid manufacturing, and a plan for reuse or disposal. Many promising studies use small samples in controlled containers. Moving from a beaker to an ocean is not a change of size alone. It is a change in nearly every condition. Aerogel cleanup may prove most practical in smaller industrial spills, workshops, chemical plants, or controlled water treatment systems where the material can be contained and recovered. It could also serve in reusable filters that continuously separate oil from water. The same principle can collect organic solvents after a leak. A porous carbon material can draw in the solvent while remaining on the surface of water. The liquid can then be removed from the aerogel and treated separately. These applications reveal a useful difference between silica aerogel and aerographene. Silica aerogel is most established where heat must be controlled. Aerographene is attractive where heat, electricity, pressure, and chemical absorption must be combined. The two families can also work together. Silica provides thermal resistance. Carbon provides conductivity and light absorption. Polymers provide flexibility. Fibers provide strength. Metal oxides provide chemical activity or energy storage. A future product may contain several types of aerogel arranged in layers. One side could face heat, another could detect damage. An internal region could absorb a leaking liquid. The material would no longer be a single block with one record-breaking property. It would be a system built from several porous networks. That movement from isolated samples to integrated systems is already changing the way aerogel is used. The pale block on a flower is memorable, but commercial insulation often looks like a dusty grey blanket. The aerogel collector on Stardust was held inside an engineered frame. A graphene pressure sensor requires wires, electrodes, and protective layers. An oil sorbent needs a method for deployment and recovery. The surrounding equipment may be heavier and less elegant than the aerogel itself, but it is what allows the unusual structure to perform a useful task. Real technology is often like that. The celebrated material sits quietly inside a collection of ordinary supports, seals, cables, fabrics, and fasteners. Spacecraft, factories, buildings, clothing, energy devices, sensors, filters, and cleanup systems all ask different things from aerogel. No single version can answer every request. Each application changes the pores, the surface, the reinforcement, and the way the material is packaged. The most important work now is not proving that aerogel can do something once. It is making sure it can do the same thing repeatedly, safely, and at a cost someone is prepared to pay. That brings the story toward the design still taking shape. Manufacturing methods are becoming faster. Aerogels are being made from plants, recycled carbon, and less expensive chemicals. Researchers are printing structures, combining multiple functions and trying to preserve extraordinary performance outside carefully controlled experiments. What begins as insulation around a rover or a dark sponge lifting oil from water may become part of a much larger change in how materials are built, with less matter placed more carefully and empty space treated as something to engineer rather than something to fill. The future of aerogel will probably not begin with a floating city, an invisible spacecraft, or a chair that weighs less than the person sitting on it. It will begin in much less dramatic places. A factory will find a faster way to dry a wet gel. A window company will make a panel that is clear enough, strong enough, and affordable enough to install in an ordinary building. A battery manufacturer will place a thin insulating layer between cells. A spacecraft engineer will replace a heavy component with a lighter, porous one. None of these events will look like a revolution on its own, but together they may decide whether aerogel remains a specialist material or becomes something used every day. The central problem is no longer proving that aerogel can have unusual properties. Scientists have already produced samples that are exceptionally light, highly insulating, electrically conductive, absorbent, flexible, transparent, or resistant to compression. The harder task is producing those properties reliably in large objects, at reasonable cost. without using more energy and chemicals than the finished material can justify. This may sound less exciting than setting a new density record, but manufacturing is where promising materials either become useful or quietly disappear into research archives. A small sample can be made with great patience. Every temperature can be controlled. Every solvent exchange can be given as much time as it needs. If the sample cracks, the experiment can be repeated. A factory does not have that freedom. It may need to produce hundreds of panels, rolls, blocks, or shaped components every day. Each one must have similar density, strength, pore size, and thermal performance. A process that takes several days may be too slow. A pressure vessel that handles one small batch may be too expensive. A solvent that works well in a laboratory may be dangerous or difficult to recycle at industrial scale. For traditional silica aerogel, drying remains one of the largest obstacles. Supercritical drying can preserve a very fine pore structure, but it requires pressurized equipment and careful control. Future production is likely to rely increasingly on methods that work at ordinary pressure, use safer liquids, shorten the number of washing steps, or allow solvents to be recovered and reused. Ordinary pressure drying is already possible for some aerogels. The challenge is reducing shrinkage and cracking while keeping the material light. Scientists can strengthen the gel before drying, change the chemistry of its surface, or choose liquids that pull less strongly on the pores as they evaporate. A successful process does not need to preserve every pore perfectly. It needs to preserve enough of the structure to meet the intended use. Insulation for a wall may tolerate more shrinkage than a transparent optical panel. An oil absorbent may work well with large irregular pores. An electrode may benefit from a combination of pore sizes rather than one extremely delicate network. This change in thinking is important. The future is unlikely to be built from perfect aerogel blocks. It will be built from aerogels designed for particular jobs, with manufacturing methods chosen to provide the properties that matter and ignore the ones that do not. Continuous production could make a major difference. Instead of preparing one sealed container at a time, a liquid mixture might be spread onto a moving fabric, allowed to form a gel, washed, dried, and rolled for transport. Fibers would support the structure throughout the process. The result would not look like the clear blue aerogel often shown in photographs. It might look like an ordinary grey sheet, which is often what useful technology looks like after the photographers have gone home. Printing methods offer another route. A thick liquid containing silica particles, graphene oxide, cellulose, polymers, or other building blocks can be deposited in planned patterns. The printed form is then gelled and dried. This allows engineers to choose where the solid framework will be placed instead of depending entirely on a random network. Printed structures can contain large channels for moving liquids, dense regions for carrying loads, and fine pores for providing surface area. The design can change from one side of the object to the other. A component might be stiff where it attaches to a machine and flexible where it experiences movement. This control may help aerographene become more practical. The lightest graphene aerogels often have random structures that are difficult to reproduce. Printing can create regular cells and predictable supports. The finished object may be heavier than a record-breaking sample, but it can be stronger, easier to connect, and more reliable. Aerospace engineers are interested in that balance. Saving weight remains valuable, but a material must also survive vibration, pressure changes, radiation, temperature cycling, and years of storage. A slightly heavier aerogel that performs consistently is more useful than an almost weightless one that loses its shape during launch. Future spacecraft may use aerogel in several different forms. Cryogenic fuel tanks need insulation that reduces heat entering extremely cold liquids. Long missions make this especially important because small heat leaks continue for weeks or months. If propellant boils away, the spacecraft loses material that may be needed for maneuvering, landing, power, or the journey home. Hybrid insulation systems can combine aerogel with reflective layers. The reflective layers reduce heat carried by radiation, while aerogel reduces heat carried through gas and solid contact. The combination can work across different levels of vacuum and provide better protection than either material alone. Reinforced aerogel may also become part of flexible heat shields used during atmospheric entry. Inflatable structures can be packed into a launch vehicle and deployed before a spacecraft reaches a planet. Their large surface helps slow the vehicle, but they need lightweight insulation beneath the hot outer fabric. A rigid ceramic tile cannot easily fold into a compact package. A flexible aerogel composite can bend with the structure and expand when it is deployed. It must still resist intense heating and remain attached while fast-moving gas presses against the vehicle. Venus creates an even harsher problem. Its lower atmosphere is extremely hot. The pressure is high, and corrosive chemicals may attack exposed materials. A lander that survives only a short time can still collect useful information, but longer operation requires better thermal protection. Aerogel composites designed for high temperature and chemical resistance may extend the working life of future Venus instruments. The insulation would delay heat rather than stop it permanently. Every extra minute before the electronics become too hot could allow more measurements, photographs, and transmissions. Aerogel is also being explored in lightweight antennas. A conventional aircraft antenna may project from the surface and create drag. A thin, aerogel-based antenna can be shaped to follow the outer skin of an aircraft or drone. Polymer aerogels can support conductive elements while adding little weight. This is a good example of aerogel doing more than insulation. The porous material becomes part of an electrical device. Its shape, flexibility, and low mass are as important as its thermal behavior. Future aircraft may carry large numbers of sensors and communication systems. Drones, electric aircraft, and other vehicles have limited space and power. A lightweight antenna built into the surface could provide satellite communication without a heavy housing or a large object sticking into the airflow. Aerogel-based wire insulation may reduce mass inside aircraft and spacecraft as well. A single cable does not weigh very much, but a complex vehicle can contain many kilometers of wiring. The insulation around those wires must prevent electrical contact, resist heat, survive movement, and release little smoke if damaged. A lightweight polymer aerogel could reduce the mass of the cable covering while maintaining electrical and thermal protection. The saving from one wire would be small. The saving across an entire vehicle could be significant. Buildings may become the largest opportunity because buildings use enormous areas of insulation and glass. The difficulty is cost. A spacecraft can justify an expensive material when weight determines whether a mission succeeds. A homeowner usually compares the price with mineral wool, foam, cellulose, and other familiar products. Aerogel will need to provide a clear advantage. One advantage is thinness. Many older buildings cannot accept thick new insulation without reducing interior space or changing their appearance. Historic buildings may have walls and decorative details that cannot easily be replaced. A thin aerogel blanket or composite panel can add insulation where ordinary products would be too bulky. It can be placed behind interior surfaces, around window frames, or inside specialized exterior cladding. The material must remain dry, resist fire, survive decades of temperature changes, and avoid releasing dust into occupied rooms. Windows present an even larger challenge. They provide light and a view, but they also allow heat to enter and leave. Adding more panes improves insulation, yet it increases weight, thickness, and cost. Transparent aerogels could fill the space between panes or form thin films attached to existing glass. The ideal material would allow visible light through, limit heat transfer, remain clear over time, resist moisture, and survive cleaning and sunlight. Early aerogels often scattered too much light. They produced a bright but cloudy view. That may be acceptable in a roof light or privacy window, but not in a living room where people prefer the garden to remain recognizable. Researchers are improving transparency by controlling pore size and making the structure more uniform. Cellulose-based aerogels and flexible transparent films are receiving particular attention. Cellulose is widely available from plants, and carefully processed fibers can form light porous structures with good optical and thermal behavior. Large clear panels are difficult because a small difference in density can scatter light. Cracks are easy to see, moisture can alter the structure. Attaching the aerogel to glass without creating bubbles or cloudy regions requires careful processing. The first widespread transparent aerogel products may not provide a perfect view. They may appear in offices, factories, roof panels, greenhouses, and public buildings where diffuse daylight is useful. As manufacturing improves, clearer versions could move into homes and vehicles. Aerogel windows could also be designed to manage different parts of sunlight. Visible light is useful for illumination. Ultraviolet radiation can damage materials and skin. Infrared radiation carries much of the solar heat. A future glazing system might allow most visible light through, while rejecting unwanted ultraviolet and infrared energy. It could reduce heat entering during summer while limiting heat loss during winter. Some designs may change their optical behavior with temperature or an electrical signal. The aerogel would be one layer in that system. Coatings, films, gas spaces, and ordinary glass would perform other tasks. Once again, the future belongs to combinations rather than one miraculous material. Vehicles offer another large area of growth, especially electric vehicles. Batteries work best within a controlled temperature range. If one cell is damaged and heats rapidly, the energy can spread to neighbouring cells. A thin aerogel barrier can slow that transfer and give safety systems more time to respond. The barrier must be light, resistant to fire, easy to place between cells, and stable through years of vibration. Silica aerogel is a natural candidate because it insulates well and does not burn like an untreated carbon material. Reinforced blankets or panels can provide better handling than fragile monoliths. The exact design depends on the battery shape and the amount of space available. Aerogel may also insulate vehicle cabins, exhaust systems, fuel cells, and hydrogen storage equipment. Reducing thickness can create more room for passengers or other components. Reducing heat loss can improve efficiency in cold weather. Graphene aerogel may take a different role inside future energy devices. Its open conductive network is useful for batteries, supercapacitors, and fuel cells, but several problems must be solved before it becomes common. The first is volume. A very low-density electrode can store a useful amount of charge compared with its own mass, while performing poorly compared with the space it occupies. A phone, car, or aircraft has limited room. Engineers care about how much energy fits into both mass and volume. Compressing the aerogel places more carbon into the available space, but it can close pores and slow the movement of charged particles. The structure must be dense enough to store energy efficiently, and open enough to allow fast transport. The second problem is consistency. Graphene sheets vary in size, thickness, defects, and chemical composition. Different batches can produce different results. Standardized starting materials and processing methods will be needed. The third is integration. The aerogel must attach securely to metal contacts. It must remain stable in the electrolyte. It must tolerate repeated charging, heating, and expansion. A successful electrode is not simply a black sponge placed inside a battery. Hybrid aerogels may offer the most realistic path. Graphene can provide conductivity. Metal oxides or other active substances can store charge. Polymers can improve strength. Large pores can provide transport, while small pores offer surface area. Future designs may be grown directly on a current collector, so no separate attachment is needed. Printing may place active material only where it is useful. Sensors within the porous network may detect temperature or strain before damage becomes serious. This combination of sensing and structural performance could become one of the most important directions. Aerogel need not remain a passive material. A graphene-based insulation layer could carry a small electrical signal. If the structure is compressed, cracked, heated, or exposed to liquid, the signal could change. A wall panel might detect moisture before mold develops. A battery barrier might notice swelling between cells. A pipeline insulation layer could report a leak. An aircraft component could track repeated vibration and warn when damage begins. The same porous framework that performs the main task becomes its own monitoring system. This reduces the need to attach separate sensors and allows changes to be measured throughout the material rather than at a few points. Wearable devices provide a smaller version of the same idea. A flexible graphene aerogel sensor can respond to pressure, bending, and movement. It may detect breathing, a pulse, joint motion, or contact between a robotic hand and an object. For medical or personal use, the material must survive sweat, cleaning, repeated bending, and contact with skin. It must provide a stable signal without becoming uncomfortable. Protective layers will be needed, but those layers must remain soft and must not prevent pressure from reaching the aerogel. The most successful products may not be made from pure graphene. A cellulose sponge coated with graphene can offer better toughness and lower cost. A polymer network can hold the conductive sheets in place. The finished sensor may contain only a small amount of the expensive carbon material. Environmental uses face the same movement toward composites and renewable ingredients. Aerogels can remove oil, dyes, metals, medicines, and other pollutants from water, but a laboratory absorbent is only the beginning. A practical treatment system must process large amounts of water without becoming blocked. It must select the unwanted substances, release them for disposal or recycling, and survive repeated use. The aerogel must not shed harmful particles into the water it is supposed to clean. Future filters may combine several pore sizes. Large channels will allow water to flow. Smaller pores will provide surface area. Chemical groups attached to the walls will attract selected pollutants. Some systems may use light to break pollutants down after capturing them. Others may contain catalysts that turn harmful molecules into less dangerous ones. Magnetic particles could allow the filter material to be collected from a tank without fine screening. Biomass-based aerogels may make these systems more sustainable. Cellulose, lignin, starch, chitosan, alginate, and other biological materials can form porous networks. Agricultural waste can provide silica or carbon. Rice husks, for example, contain a significant amount of silica. Plant fibers can provide cellulose. Wood residues and other waste can be converted into carbon structures. Turning these materials into aerogels could reduce reliance on expensive refined ingredients. The environmental benefit is not automatic. Processing biomass may require acids, bases, bleaching agents, high temperatures, or large amounts of water. A material made from plants can still have a heavy manufacturing footprint. Future research will need to examine the entire life of the product. Where did the raw material come from? How much energy was used? Were solvents recovered? How long did the aerogel last? Could it be repaired, reused, recycled, or safely broken down? This broader accounting may change which aerogel is considered best. The lightest or most insulating sample may not be the most sustainable one. A slightly heavier material made quickly from waste and reused many times could have a much smaller total impact. Fire safety will need similar attention. Silica and mineral aerogels are naturally resistant to burning, which makes them attractive for buildings, batteries, and transport. Polymer and carbon aerogels may burn unless they are protected or modified. Adding flame-resistant chemicals can improve safety, but may introduce toxicity or complicate recycling. Mineral coatings can help, but they add mass and may reduce flexibility. Every application will require a careful balance. Health and handling also matter. Many aerogels release dust when cut or rubbed. Future products will need surfaces that keep particles contained. Fibers, skins, and binders can make installation safer. The finished product should be judged under realistic conditions. It should be cut, bent, dropped, wet, heated, frozen, and aged. It should be tested after months or years, not only when it is freshly removed from the drying equipment. Standards will become more important as the market grows. Manufacturers need agreed ways to measure density, thermal conductivity, strength, dust release, moisture resistance, and fire behavior. Customers need to know that two products described with the same words provide similar performance. Graphene-based materials face an additional naming problem. The word graphene is used for sheets with different thicknesses, sizes, defects, and chemical groups. Two products called graphene aerogel may contain very different amounts and forms of carbon. Clear definitions will help engineers compare results. They will also reduce exaggerated claims. A material does not become useful merely because the word graphene appears on the label. The same caution applies to predictions. Aerogel will not replace steel, glass, plastic, insulation, batteries, filters, and fabric all at once. It may improve selected parts of each. The most likely future is less dramatic and more practical. Aerogel becomes one layer in a window, one barrier in a battery, one support inside a catalyst, one flexible section of an antenna, one sensing region in a glove, one absorbent component inside a water treatment unit. In each case, it will be chosen because its pores solve a specific problem. It may reduce thickness, expose more surface, lower weight, slow heat, carry charge, or allow controlled compression. Aerographene will follow the same path. Its record-breaking density will remain interesting, but usefulness will depend on strength, consistency, and cost. The successful version may not be the lightest one ever made. It may be the one that can be produced every day, attached to ordinary components, and used thousands of times without failing. There is something fitting about that outcome. Aerogel began as an attempt to remove the liquid from a gel without losing its structure. Its future depends on removing other things that are not needed. Unnecessary processing steps, excess solvent, wasted heat, heavy supports, empty promises. What remains must be carefully connected. A small amount of material placed where it performs the most work. Pores sized for the movement of heat, sound, liquid, gas, or electrical charge. Strong junctions where force must travel. Flexible regions where the object needs to bend. That approach reaches beyond aerogel. Material science is increasingly concerned with architecture as well as ingredients. Instead of asking only what a product should be made from, engineers ask how matter should be arranged across many scales. A bone is not a solid mineral rod. A tree trunk is not filled with dense wood from edge to center. A bird wing does not use the same structure everywhere. Nature saves material by building networks, hollow regions, fibers, layers, and gradual changes in density. Aerogel takes this strategy to an extreme. It shows that empty space can provide insulation, movement, access, and low weight when the remaining solid is arranged well enough. The next generation of aerogels may become less visually impressive as it becomes more useful. It may be hidden inside walls, batteries, pipes, aircraft, medical devices, and spacecraft. Most people may never touch a clear block of frozen smoke or a black piece of aerographene. They may simply notice that a building remains comfortable with less energy, that a vehicle battery is safer, that a spacecraft carries more equipment, or that a sensor feels almost weightless against the skin. A successful material does not need to remain visible. It needs to keep working. We began with a solid that appeared to contain almost nothing. We found that the emptiness was not a missing part. It was the main part of the design. The pores controlled heat. The walls carried charge. The folds absorbed pressure. The internal surfaces held liquids and molecules. The future will depend on learning to control those features without losing them during manufacturing. It will require better drying, safer chemistry, renewable ingredients, stronger composites, consistent testing, and honest decisions about cost. Some ideas will remain in laboratories, others will find small specialist markets. A few may become ordinary enough that their unusual origin is forgotten. That is often the final sign that a technology has succeeded. It no longer needs to be introduced as a wonder. It becomes a window, a blanket, a sensor, or a protective layer that does its job without asking for attention. And now, after moving through smoke like silica, folded carbon sheets, comet collectors, cold fuel tanks, pressure sensors, and possible windows of the future, we have reached the end of this particular journey. Perhaps the object nearest you still feels solid and familiar. A table, a wall, a phone, or the bed beneath you. Each one seems full of matter, but every material is also an arrangement of spaces and connections. Aerogel simply makes that fact easier to see. If you found this slow look at one of the lightest families of materials soothing or interesting, you can give the video a like and subscribe to Physics with William. It helps this quiet collection of science stories reach other people who may enjoy learning about graphene, space travel, unusual matter, or why a block of nearly empty material can require such a surprisingly full explanation. For now, there is nothing left to manufacture, compress, dry, or place inside a pressure vessel. The aerogel can remain where it is, holding its shape with very little material and a great deal of carefully arranged space. You can let the questions settle, let the machines in the laboratory go quiet, leave the spacecraft insulated, the windows closed, and the carbon framework resting inside its pores. Sleep well, fellow traveller, and thank you for spending this time with Physics with William.